Hey folks, how's it going? Give me a sec to set these things up. Doing things, doing stuff, calculating. Oh, there we go. Let's see. Oh, wrong thing. There we go. Nice. Okay, now we're mostly set up. Hope everyone's doing great. Let me see. Let me close this. That's not closed. Let me close this. There we go. Yeah, today I wanted to do a couple of things. I wanted to check out a video about Fil-C, and I also wanted to do some coding on Jank. We're going to do both of those. So I think the only thing we need to do before we can jump into that is I need to drop a couple of notifications. On the various places. All right. There we go. Places encountered. Nice. Let's check this out. So obviously we've talked about Fil-C and Phil before on stream, but someone just linked this video to me, and I saw people discussing it on Twitter. It came out within the last week. So we'll take a look. I want this thing to go away though. This thing right here, this pop-up video thing. How can I make that go away? I don't want that. Maybe it'll just
Thanks,
go away
Isaac.
on its own. What if I click it and then I undo it and then it goes away? Maybe. All right. All right. Let's check this out. Let's see. Is this in the way? Yeah. So if I do theater mode, then you guys aren't going to be able to see. So I'll not do theater mode, and then we'll watch it like this. And then also you guys should be able to hear this just fine, because I have selected that you can do that.
Yeah, so let's talk about Fil-C. So what is Fil-C? It's a totally memory-safe implementation of C and C++. What I mean by that is if you take a C or C++ program, compile it with my compiler, then the resulting program is strictly safer than if you had rewritten it in any other memory-safe language. So that's the memory safety definition. I'll go into exactly what I mean by memory safety here in a little bit, so you can get a more formal take on what I mean by that. And as I'll hopefully convince you in this talk, it is fanatically compatible with C and C++. So tons and tons of C and C++ code work in Fil-C out of the box or with just minimal changes. I think roughly half of the software packages I've ported to Fil-C just work out of the box. I just point them at my compiler and it works. One of the things that's the catch is it's a personal project, so there's some gotchas. One of them is that it only works on Linux x86 64. But hey, I mean, I'm working on it in my spare time. If that's the only thing you don't like about Fil-C, then like send patches. So the agenda for this talk is, I first want to define memory safety. I think different people define it in a different way, and that's fine. I'm going to give you my definition so we're on the same page. Then I'm going to review the prior art. There's been a lot of attempts to make C memory safe, and none of them really worked out. I think of all of them, Fil-C has the most users. So I want to review how the prior art looks. Then I'm going to tell you the key idea behind Fil-C, as well as then going into the details of the compiler and the runtime. And at some point throughout this talk, I promise there will be a demo. So what is memory safety? I kind of like this definition. In a memory-safe programming language, memory logic bugs don't give the attacker control over all of memory. So what's that all about? So examples of how the attacker might get control over all of memory. Let's say that you're
his slide transitions are like a real callback to like middle school when I was like doing word art, and every slide had a different transition, slides and wipes and radial spins. I haven't seen this stuff in a long time. It's silly. It's interesting. It's a bit of character for him to put that in there. I think it says something about him as well.
Using YOLO C, which is what I call the C that's not the Fil-C. If you're using YOLO C and you fail to check array bounds and you use an index that's user-controlled, attacker-controlled, then the attacker could supply a very large index that essentially turns that array index access into an access of anywhere in memory that they like. So that's a case where the attacker suddenly gets to control all of memory. Another example is type confusion. If the attacker finds themselves in a position where they can store an integer of their liking into memory,
hey, Johnny,
knowing that the program will load that integer as a pointer and then use that pointer for dereferences, then by storing integers that are addresses, they can make the program access whatever memory they like. These are memory safety bugs. These are the kinds of things we want to prevent. There are many other bugs that are kind of like in this vein. So why is this bad? I want to give you like a vivid taste of why it is bad. Starting in the 1980s, you started to see attacks that would use memory safety vulnerabilities to just write machine code into memory. This is called shellcode. You have a stack smasher where someone's got a buffer on the stack. You overwrite the buffer with machine code and a return address that points at that machine code. Now all of a sudden your program is just executing whatever machine code the attacker wanted. People realized this was bad, so a bunch of mitigations against that landed, including address space layout randomization and the no execute bit. But then attackers very quickly found a way around this. It turns out if you don't attack the problem at the source, namely controlling all of memory, attackers are still going to find a way to get full control over your program. The way that they do this, even if you prevent them from writing machine code into memory, is that they overwrite the stack with what's called a run.
So an interesting thing about this, if this is something you guys are interested in, there's there's some really fun like hacker war games around exploiting certain programs in this way on machines that very specifically don't have like address space randomization enabled and whatnot. My favorite one is a game called IO war game. Yeah, this one. And unfortunately, they don't have TLS certs because nobody does from the old hacker websites these days. But the thing is, this you don't play this in a browser anyway. You play this by SSHing into an actual machine, and so you SSH in as level 1, and they give you the level 1 passphrase, and then it's your job to get to level 2. And the way that you do that is that within level 1, they're going to have a program that you can run. And that program has the permissions of level 2. And so at that point, it's your goal to exploit that program such that you can well, it depends on the program. Sometimes it's going to do a passphrase check, and you just need to like make that work. Find out what the passphrase is by reverse engineering it or something like that. But also sometimes it's a buffer overflow, and you need to write in some shell code or something like that so that you can get a shell. And that shell, since that program belongs to level 2, let's say, when you start a shell from that program, you end up getting a level 2 shell, at which point you can get the level 2 passphrase, because the passphrase for each level is stored within the home directory of that level as well. And there are so many different like types of attacks that you need to do for each of these, and they kind of give you some tips for like how to research what you're trying to do. Some of them you're specifically triggering like MD5 hash collisions, and in others you have like a single byte for an overflow that you can write. You can only write a single byte, and you have to choose where in memory am I going to write that single byte. And I will not say any more, because that was a really fun one to try to find out, like, if I could only change one byte, in order to get me to the next level, what byte does that need to be? Yeah, there are a whole bunch. It's really fun. I don't know if people do this sort of thing these days, but it's such a great, I did these a lot when I was a teenager, and then going through college as well. It was such a fun way to learn about systems, in particular Linux systems. But this is also very related to what he's talking about with the types of attacks that people do. You want to have a reverse engineering course your next semester? Oh, nice. Yeah, I hope that you can, and that you enjoy that. For me, reverse engineering is a blast. It's a blast. I used to do that. Like, it's harder to find communities of people doing that these days. It's also, I have a lot less to reverse engineer these days, because I haven't used Windows in over 15 years. But back when I was on Windows, and everything has licenses and key codes and everything like that, you have a lot more that is practically interesting to try to reverse engineer. And on Linux, with everything just being free open source software, I find I have fewer opportunities where I'm like, I really want to reverse engineer this thing. Anyway.
Chain, where they keep pointing return addresses at anywhere in your code that they like, stitching together different parts of your program to basically make your program do whatever they want. And this is like fairly straightforward to get to the point where the attacker can just make your computer do whatever they want it to do. So people realize this was bad. The story continues. Again, the more mitigation.
Oh, right. The reason I paused was actually not to talk about the IO war game. The reason I paused was to talk about, so basically what he's describing is along the lines of the mental model that people who like the JVM have, right? Where they're just like, yeah, I want a programming environment where I just don't need to worry about things like memory safety and buffer overflow, security concerns, and everything like that. And on the JVM and on the common language runtime, the CLR, like, people in general, they just don't worry about those things. Now, part of that is because those languages, Java and C# in particular, are more memory safe than like C and C++. But also part of it is just that the whole platform that those applications are running on gives them a lot more trust. Gives them a lot more. that they can build upon in terms of just not having to worry about those things. And in the native world, where you're just running machine code, like the only thing between you and the machine is the operating system, and that the operating system tries to be, you know, as thin as it can be in most cases. So to have like Fil-C, and in particular like Fil-C's runtime in between you and the operating system and the actual hardware is a lot, to me anyway. It seems a lot like the sort of cushion that you get with a virtual machine.
Applications landed like CFI, pointer authentication, to try to prevent attackers from writing code addresses that end up working. But then all that attackers do is that they just overwrite sufficiently critical data to make your program do whatever they want. The point is, if the attacker can access all of memory, then you've already lost, and there's no point in having any other mitigations. So here's an example of a modern attack that doesn't involve overwriting machine code, doesn't involve a ROP chain, doesn't involve overwriting any code pointers whatsoever. So you've got a program. Somewhere in that program, there's a parser. Somewhere else, maybe for the purpose of this example, another thread. There's a thread that's going to call POSIX spawn, which is the system call on Unix to start another process. And it's going to have a command buffer that it fills in. Not with the user's data. It's filling it in with like whatever the program needs. So the user isn't meant to be able to control the command buffer. But your parser has a bug, and that bug allows the attacker to write anywhere in memory, so the attacker overwrites the command buffer. Now all of a sudden your computer program is doing not what you wanted, but whatever the attacker wanted. So this is an example of how modern exploits defeat like basically all of those mitigations that I had on the previous slide. But it gets worse. There's a thing people call weird execution. Basically, if you look at like what your program is and zoom in to what's going on in the millions of machine code instructions, what you're going to see is branches that depend on memory. That's like your program at a high level. It's just a bunch of branches that depend on memory, millions of them, both from your own code and from all your dependencies. So if the attacker can control all of memory, they can use all of your branches that read from memory to send your program on whatever journey they want, and essentially stitch together the different sequences of your program to write whatever program they want your computer to execute. So the goal, prevent the attacker from controlling all of memory. We want to be in a situation where if you've got a bad array access, the worst thing that can happen is you're accessing the wrong index in that array. Or if you have a use after free, the worst thing that can happen is your program immediately crashes. That's the kind of thing we want, not that they control all of memory. So this is not a new idea. People have known that this is something that we should fix in C for a long time. So I think the earliest attempts were in the 90s. There's a bunch of them. So the first major one was called Fil-C. You can still download it. It doesn't actually support all of C. It doesn't support C++, doesn't support threads. Not sure how well it works. There's modern approaches like sanitizers. So most of these approaches aren't actually memory safe. For example, in sanitizers, all that the sanitizer is checking is that you aren't accessing a deallocated region of memory. If you access any valid region of memory where there's some object that is currently live, not yet dead, it'll just let you do it, which is exactly what the attacker wants. When the attacker controls all of memory, they want to access the live memory. So a lot of these approaches don't actually give you memory safety. They're just good for catching bugs, or they maybe like make the attacker's job just a little bit harder. The remaining approaches, like Fil-C, don't actually support the full C and C++ languages. These approaches actually don't support C++ at all, and when it comes to C, they don't support threads, they don't support GCC and Clang extensions, they don't support pointer integer unions, or actually any interesting unions in some cases. So they're not actually compatible. So I think that's why a lot of these approaches either failed or have never been used as an actual production defense to make software more secure. Well, I guess there's MTE and MIE, which is being used, but that's a probabilistic defense. So the attacker has like a 1 in 15 chance of bypassing the mitigation. So it's like, I mean, it's better than nothing, but it's only a probabilistic defense. So that only leaves Cherry standing, And the problem with Cherry is that it's hardware that you can't buy. And the problem with the problem with designing programming language technology around new hardware with special instructions is that the special hardware is going to trail commodity hardware in performance by such an amount that I've got this cheap Dell laptop. I actually really like it, but it was like the cheapest one they had. Running Fil-C on this laptop will give you better performance than running on the fastest Cherry hardware you could ever buy. There's just nothing that you get out of having the special hardware. And anyway, you wouldn't be able to buy it. So I don't have to worry about it as a competitor. So what is the idea that started Fil-C? As Isaac said in the introduction, my job is that I'm a pointy-haired boss. I approached this problem partly as a manager. So scoping the problem was really important to me. And then there's a trick. So a lot of it is I've been thinking about this for a long time, and I came up with a really cool trick. So let's scope the problem together. So here are possible goals that you could have for a memory-safe implementation of C.
So one thing, just because I like doing this while I'm watching anyone present, including myself, you'll notice that Phil says a lot, and I do this in particular. I say a lot when I don't know what I'm about to say. So if I'm going to give a talk, generally what I'll do is I won't write a script necessarily, because when you write a script, you are limited directly, to those words. And if you go off the script, then all of a sudden you just crash. But if you do the talk enough, and you actually talk, in my experience anyway, this works for me, but if you do the talk enough, and you say exactly what you want to say over and over, like couple dozen times, then when you actually give the talk, you don't have to think about what you're saying. If I went up and I gave a talk on anything, even something I knew very well, like jank, and I didn't prepare at all, I would have a lot of ums, because I would just be trying to figure out how to string all of my sentences together. And some people, maybe that's not why they do it. Like some people are more nervous. Some people have speaking tics or whatever. But as something to think about when you're going into your own talks, if you're like, I want to avoid ums, well, the best thing to do, the first thing to look at is how well do you know what you're actually going to say? Not necessarily how well do you know the topic. Obviously, Phil knows this topic better than anybody. Just like I know jank better than anybody. But knowing the topic is not the same as knowing what you're going to say, the ideas that you're going to convey, the narrative that you have, and how you're going to string all those sentences together. And the only way that you can do that, and people really don't like doing this, the only way that you can do that is to actually just give the talk over and over and over again and record it. And then when you record it, you listen back. The reason why you record it is a lot of people, when they're practicing a talk, they'll not actually give the talk like they would in front of other people. And maybe they'll do a little bit in their head, just like, oh yeah, and then I'll say this bit here, or they'll make a note to themselves or something like that. It's very different than actually just giving the talk. So if you record yourself and then actually just give the talk and then listen back afterward, find out which parts you like, which parts you don't like, where you paused, where you struggled, then you can smooth out that whole thing so that when you finally give the talk, it's really smooth, very minimal ums. It's just like a really great narrative. I don't know Phil. I don't know how his brain works. So maybe he does all that, but still has lots of ums. So no shade on him. But if it's something that you're thinking about for presenting yourself, that's something to keep in mind.
I actually decided the first thing that I noticed using my manager hat is there's too many goals. because we haven't actually achieved even a subset of these goals yet, so the first stab needs to be something that achieves some of the goals. That's important, because Fil-C might go down in history as merely a stepping stone to a better technology that will build on what I did in order to achieve the rest of these goals. But I'm just scoping it so that I can give y'all something meaningful instead of just like an academic exercise. So the goal that I eliminated outright is the goal of binary compatibility. What this means is that when you compile with Fil-C, you can't dynamically link with things not compiled with Fil-C. You can dynamically link Fil-C with Fil-C, but you can't dynamically intermix. So that's just like a non-goal. Supporting that would be a lot of work that I just haven't done. And then when I first started out, I said to myself, you know what? I don't care how fast it is. I don't care how slow it is. I just want it to be memory safe and compatible. The first version was 200 times slower. It's not 200 times slower anymore. It's like median 4 times slower. I think Dr. Hipp says it's 6 times slower for SQLite. There's some situations where it's actually really fast. I benchmarked the Blake 3 implementation in Fil-C and compared it to Blake 3 in Rust, and Fil-C was actually faster, reason being that Fil-C has better SIMD support. So huge range, anywhere from a little bit faster than Rust to 6 times slower. But in the demo, I think will convince you that it's fast enough for like everyday use. Okay, so what's the trick? Because the trick is really about making this an economical change to LLVM in the runtime that I could do in my spare time. So the key observation that I made at some point is I don't need to write a whole new compiler from scratch, because something that I get from the way that Clang and LLVM are architected is that the LLVM-IR that is produced by Clang, but right at the moment when it's produced, before it's actually optimized and transformed by the LLVM pipeline, is remarkably well behaved in how it uses pointers. It uses pointers in a way where the original intent of the programmer is largely preserved. Namely, if the programmer had a field in memory that is pointer type or reference type in C++, that gets turned into a PTR type in LLVM-IR. If the programmer had a field in memory that's not...
Yeah, you don't typically notice them, but now it's the only thing you hear. Yeah, that was intentional, because I think it's, well, in some ways I'm sorry, TJ Blue, that now you have to hear all that, but also in other ways I'm not sorry, because I think it is an important thing to hear, not only in other people, but in your own speech.
A pointer, not a reference, it would use some other LLVM type. So by reading the LLVM-IR, I know where the pointers are. As soon as I run any LLVM optimization, that stops being true, but right at that moment, I know where the pointers are. So the trick is that I instrument all of the LLVM PTR operations with invisible capabilities, or invisicaps for short, and so that each pointer carries bounds, and all pointer operations preserve the bounds and check the bounds. The bounds means that, what this means is that you, as the user of LLVM-IR, or C, will perceive the pointer as just being its raw pointer value. It'll be whatever combination of bits you put in there. But somewhere, for each pointer that you see in your program, somewhere out there, there will be a lower bound and upper bound, and some bits that determine what you can do with the pointer. But where do we store the bounds? This is the important thing, because if we stored the bounds somewhere where you have access to as a Fil-C programmer, then you could just corrupt the bounds, and then the attacker gets control over all of memory. So the bounds have to be stored somewhere where you can't actually mess with them, hence invisible capabilities. How does that work? All right. When you have a pointer that's in flight, meaning it's in your local data flow, then it's represented as a 64-bit int val, as I call it. It's the pointer's integer value. It's the untrusted value, the value you see and that you control, combined with a lower. This is the lower bounds. You don't get to see it. You don't even know it's there. It's just kind of flowing with your pointer in local data flow. And it's just local data flow, so forget about memory for a minute. This is when it's like in a register. It's in 2 registers instead of 1. The lower the lower bounds, in addition to pointing at the lower bounds of that object, at the lower bounds of.
So Fil-C relies on implementation details of how Clang generates unoptimized LLVM IR. Yes. Hey, Phronophobic. So my understanding is that Phil forked Clang, and he's maintaining a fork that last I saw was on like 19, Clang 19, and then he was trying to, or maybe it was on Clang 20. He was trying to update it to Clang 22, and so he's doing the work of rebasing his changes on top of the upstream Clang LLVM. But yeah, I think he's forked that and then is using the IR that Clang generates to then basically run passes over that IR in order to do the fill magic. It makes a lot of sense. It is wild. I mean, like, what he's doing is crazy, and I'm not trying to be reductionist at all, but it makes so much sense that he built on top of Clang, especially since he's not trying to solve this at a language level. He's trying to solve this at a compiler level. There'd be no point in implementing his own C and C++ compiler and having to deal with all of the bullshit that is C and C++, just so that then he can focus on the back end of compilers. So for those of you who don't know, compilers, within the compiler space, we also have front end and back end developers. Where front end is, compiler front end is like Clang. And so compiler front ends deal with the source code, and their output is generally some sort of intermediate representation. So in this case, Clang outputs unoptimized LLVM IR. And then LLVM is the compiler backend, and it consumes LLVM IR, and its job is to optimize it and then lower the LLVM IR down to whatever the target machine code is. And so that could be x86-64, or it could be ARM64, or it could be MIPS or something else. And there's a very clear separation there. That's really great for LLVM because it means that Rust, for example, Rust is also a compiler front end that generates LLVM IR. And then it just gives that LLVM IR to LLVM. LLVM does its same optimizations and lowering in the same exact way that it does with Clang. And so Phil is building on top of all of that and just getting right in the middle, in between Clang and LLVM, and in between the front end and the back end. And he's injecting some of his magic there. I think that there's a lot more going on than just that, but that's what he's talking about so far. Wonder if it would make sense to include Fil-C and LLVM directly behind a flag. Yeah, I don't know what his upstream goals are, but I think that we should all be hoping that this work is somehow upstreamed into LLVM at some point. I think he's still figuring things out, and I know I've certainly read, he's talking about InvisiCaps here. I've read about all of the predecessors of InvisiCaps as he's been trying to figure out how to actually do these things. And so I don't know if he's at a point where he's like, yeah, this is for sure the final design. We want to try to get this upstreamed, or if it's just still an open research problem and maybe the design's going to actually change quite a bit. We'll have to see. But yeah, I really hope that this ends up just being in LLVM, because it's something that everybody who's on LLVM should just be able to target, right? So in that case, you could use Rust if that's the language that you like, if that's the language that you prefer. You could use that and then still end up getting the Fil-C sort of injected into your LLVM IR. Or you could use C or C++, or you could use any other language that's on the LLVM toolchain, including Jank. Does Fil-C generate code that can never segfault, or does it solve just the most common issues? Pointers are absolutely everywhere in C and C++. So Johnny, what Fil-C does is that it provides a runtime to make it so that whenever you try to do something that would segfault, it either falls back to well-defined behavior, such as like, oh, I accessed some uninitialized memory or something like that, or I reach beyond the bounds of this array or something like that. It either, in some cases, falls back to well-defined behavior, such as like, okay, we're just going to give you back 0, or some sort of like safe in the sense of not giving attackers control, some sort of safe approach like that. Or if there's no sort of safe fallback that it can do, then it panics. And there's a very big difference between panicking and segfaulting. And so, unfortunately, Phil, because we all do this, Phil still uses the terminology crash, which is to say, like, you know, in the worst case scenario, well, we're just going to crash. But there's a very big difference between a panic that stops your application and a segfault which crashes your application. Because a segfault means something went wrong in terms of like memory safety, and the OS killed your application. But what can happen before a segfault is everything that he was just talking about before, which is the attacker gets complete control over your process and gets to execute whatever code they want. So I think that the main goal here, to summarize, is Fil-C takes all of those unsafe operations that would segfault or would be undefined behavior, and either tries to turn them into well-defined behavior if it can, or in the worst case, just panics. Hey, Heldiana. Welcome. Hope you're doing great.
That object to the left of those lower bounds is the capability header, where you will find the upper bounds. So if you have the lower bounds, you can find the upper bounds. And another word, the aux word, that stores some extra stuff. No capability ever produced by any allocation in Fil-C ever has its lower and upper bounds around any of the red stuff. So you don't ever get to modify the lower bounds. You don't ever get to modify the upper bounds. And then if you store pointers into this allocation, then the auxiliary word ends up pointing at
Panic equals well-defined prevention of an unrecoverable error. Segfault equals someone may have tried misusing wrong memory management. So when we say panic, so panic is used quite often in compilers. You'll see it in Rust, and Phil talks about it, and then Jank has panic as well, actually. That just means stop. That just, like, you're just going to terminate the program. So you find that something is wrong, and it's something that should definitely not be the case. And at that point, you can't trust anything. You just need to stop. But you stop in a controlled way. And with Fil-C, in those cases, when you panic, you're not giving control to the attacker at all. You're just saying, this is not right. There's no way this is right. We're just gonna stop. Yeah, yeah, exactly. We call it panic instead of terminate. So in Jank, in C++, there is a function called terminate, and this is what will be called in Jank's panic function. This is also exactly what's called if you have an uncaught exception. So if an exception is thrown and not caught, then it's going to call terminate as well. So but Rust calls it panic, and then allows a program to terminate immediately.
An auxiliary allocation that has the lower bounds for every pointer stored into that allocation. Let me walk you through that with an example, because that is a little confusing. It's confusing because it's like literally the trick, right? So let's say that you malloc something. That's what you're going to get. Your int val is going to point at the bottom of this object, so is the lower. All allocations are zero initialized in Fil-C. There's no way to not get them to be zero initialized. So you're going to have zeros in there.
So for those of you who don't know, that's also a big change. Normally when you allocate some memory, it's not zero initialized. It's not initialized at all. And so you don't actually know what was there. This can be exploited based on knowing how allocators, like how a particular allocator for a program works. Because if you allocate some memory and then you free that memory and then you immediately allocate some memory of the same size, you're most likely to get back the exact memory that you just had. And that can be a problem as well, especially if that has some data in there that you didn't want people to know. Then, you know, like now they can, as long as they know when you're freeing that struct that has that data, you know, they don't want to know, they could allocate the struct of the same size and then start taking a look at that data. That's, you know, like that's just a example off the top of my head, but also it's a problem in the sense of if you try to access any of that data, if you try to read any of the, so he's allocating 16 bytes. If you try to read any of that data before you have written to it, then that's in the C spec, that's undefined behavior. And that's a problem as well. And so he's removing all that undefined behavior by just saying, okay, well, when we allocate things, it's zero initialized. And so if you start reading it right after allocation, that's not going to be a problem. And so this is one of those cases where he's taking what would have been undefined behavior and he is turning it into, you know, he's not panicking if you try to read it. He's just zero initializing it, and now it's no longer undefined behavior. You guys are just getting into the linguistics here.
And then let's say we store the current most popular number with my kids, 6, 7, into this object. So because you're storing a primitive, that's just really simple. We bounce check and we let you do that store. But what if you store another allocation? Let's see that animation again. Just so, yeah, look at that. What a cool animation. So what's happening is we're allocating this other object, and then the int val for that pointer is stored in that blue area, the payload of the object that you get to see. And its lower bounds is stored into the auxiliary allocation. And because we didn't have an auxiliary allocation already, we created one. So this incurs a 2x space overhead for those objects that have any pointers. Does not incur space overhead for objects that don't have pointers. So if you have like a frame buffer, that's not going to incur the 2x overhead. If you have a string, not going to incur the space overhead. But if you have like, I don't know, a binary tree node, then you need twice the memory. So C and C++ code sees 64-bit pointers. My compiler makes you believe that you're on an x86 64 machine, because you are. So 64-bit pointers checks out. Size of void star is 8. You don't have to change your code to adapt to different pointer sizes. And there's capability bounds flowing around with your pointers. It's just they're invisible to you. You can't modify them, and so therefore my runtime gets to trust them.
Yeah, so he's actually changed the size of pointers in memory to where instead of just 64 bits for a pointer, you actually have the 64 bits plus whatever that lower is, which is probably another 64 bits. And that's that 2x. So that means that when you're passing pointers around in your Fil-C program, they're actually twice the size. But he's changed the compiler so that way the size of the pointer still reads inside of your code as though it were 64 bits. But he's also changed it so that whenever you're doing like pointer arithmetic, if you start with one pointer and then you increment that pointer to go to the next one, normally the pointer would move forward 64 bits to get to the next pointer. But in this case, it's going to have to move forward 64 bits times 2. And so it's kind of an odd disconnect between the size of the pointer as well as pointer arithmetic. I wonder if this would break things that are trying to calculate the distance between pointers. Yeah, I wonder how he handles that. I mean, he must.
So the trick behind Fil-C, LVMIR instrumentation for the PTR type, using invisible capabilities that preserve the pointer size and prevent tampering with the bounds. That's how it works. So that's Fil-C like in a nutshell. Now let me go into the details by telling you a little bit about the compiler, and then after that telling you a little bit about the runtime. So the current compiler actually does optimizations. I've taken some amount of LLVM's optimizations and made them work with the capability model. And I run them before I run my instrumentation. The optimizations that I run include things like inlining, constant propagation, basically all of the major LLVM optimizations that you would expect. Not all of them yet, though. There's still more optimizations I could add. But I add them once I determine that they're safe to add. And the instrumentation is called the Pislinator because why not? It's a personal project. I get to name it. And that implements garbage in, memory safety out semantics, meaning that whatever LLVMIR shows up at Pislinator's doorstep, either Pislinator will refuse to compile it by crashing the compiler, or it will emit code that has all of the checks necessary to make sure that that LLVMIR is obeying Fil-C's laws of memory safety, which means capabilities to objects, pointer can't write out of bounds of the capability of the object it was allocated to point to, that kind of thing. And then after that, I run just a normal LLVM optimizing pipeline. So yeah, every side effecting operation is instrumented with runtime checks. Operations that can't be checked are just rejected, and there's no escape hatch. This is very important because in some memory safe languages like Rust, there is an escape hatch unsafe, and you're expected to use it. Fil-C has no equivalent of that. Additionally, recall that Fil-C has no dynamic linking to YOLO land, but it does have fanatical compatibility. So what that means is, whereas like if you're a Go user or a Rust user or a Zig user, if you need to use some C++ library, you're going to use the YOLO version of that library, and so you're going to end up having a process that has memory unsafe stuff in it. But if you're a Fil-C user, you're just going to take that library and compile it with Fil-C. So your whole stack is going to be memory safe. Hence, Fil-C, weirdly, despite it being C, is the most memory safe programming language in existence today. Kind of cool. So features of the compiler, it is just...
There should have been an applause there, and there was not. And I suspect that this means that people are unsure. People are maybe not convinced, or they're tentative, but that was definitely the place where applause should have happened. Because he's basically saying like, yeah, I mean, I've just made the most memory safe language. In particular, I've just made the most memory safe language runtime, and it works with basically all of this code that's already been written in C and C++. that deserves applause, my opinion.
Just a fork of Clang, 20.1.8 is the last rebase that I did, so it supports C23, C++23, almost all Clang and GCC extensions, full SIMD support. It even supports inline assembly. If you have an inline assembly snippet, I run a static analysis over it to make sure that it's not doing side effects that would violate the Fil-C model. If it doesn't, then I allow it. So like a common idiom in SIMD code like Blake 3 is that you use SIMD intrinsics for your actual math, but use inline assembly for CPU detection using instructions like CPU ID, xgetBV, maybe some other stuff. That kind of inline assembly that does CPU ID is allowed by my compiler because it doesn't perform harmful effects. Well, I actually check to make sure it doesn't perform harmful effects. Like, you could do CPU ID and it clobbers the A, B, C, and D registers. If you fail to list that as in your clobber list, the Fil-C compiler will reject it. So it's actually doing like the checking that your inline assembly is not completely busted. And it's just Clang. So if you want to build something with it, you just point your build system at it, and it just works. And it is like really compatible. So it's not that I'm like crashing your program on undefined behavior. I like think undefined behavior is BS. Like I use all the things that the spec says I'm not allowed to use when I'm a C programmer. And I want that kind of code to be able to work in Fil-C. So Fil-C does not enforce strict aliasing. Integer overflows wrap. You can bitcast through unions. You can race all you like. If you race on a pointer, it won't violate the memory safety. You'll just get a bad outcome. So like real C code works in Fil-C. It's not just the C code that's written to conform to the spec, because nobody writes C code that conforms to the spec. Now let's talk about the runtime. The most controversial part of the runtime is that it uses a garbage collector. So I want to talk about that a little bit. It's an interesting choice. And then the rest of the runtime is meant to make it feel like a conventional Linux, C, or C++ runtime. I use either the musl or the glibc libcs that are compiled to Fil-C, and the rest of the userland compiled with Fil-C. So you get the experience that you would get if you were just like programming in C or C++ on Linux. So why garbage collector? It gives me the most deterministic possible answer to what happens on use after free. In Fil-C, if you free an object and then you try to access it, it's a panic. And it will continue to be a panic forever. There's no amount of heap grooming or trying to allocate enough memory to use up a quarantine or whatever that will make it not a panic. It'll forever be a panic. There's no way use after free, you're keeping a dangling pointer around for as long as you like. No way that's ever going to cause any kind of thing other than a panic.
GC isn't for userland here, right? What do you mean, DJ Blue? All this is userland code. I think that the GC is used as, I don't know, I guess we're going to have to see. But my impression so far is that he is hooking malloc so that way every dynamic allocation goes through his GC.
And because Fil-C has comprehensive memory safety and capabilities that are trusted, I'm able to implement an accurate garbage collector. It's not a conservative garbage collector. It's an accurate garbage collector like what you would find in a Java VM. And I'm a garbage collection person by trade, so I wrote like a really good concurrent garbage collector that has no pauses whatsoever. So it's an accurate garbage collector. It's parallel, so it'll use multiple cores when it has to run. It's concurrent and on the fly, meaning it never pauses the program. It's non-moving, mainly so that if you do a pointer to integer cast multiple times, you always get the same answer. And it has what I call turbo sweep, which is a bit vector SWAR algorithm for sweeping. So the sweep is really, really fast. In addition to running on multiple cores, each loop cycle of the sweeper is actually sweeping multiple objects. Now, could you make a Fil-C without a GC? The answer is you absolutely could. You would follow the Cherry route. Cherry has a no GC mode. That's how most people run it. The idea is that if you have a use after free, then that capability now points to the same region of memory that it pointed to before, but now there's just like a different object there. Most security folks that I've talked to don't believe that that is exploitable so long as the thing that ends up in that memory region isn't the metadata that you want to keep trusted. So you'd have to do some allocator tricks to make sure that you, for example, never allocate the trusted metadata inside of regions that were reused from user data and vice versa. But you could totally make a Fil-C without a GC. I chose not to, because I'm a GC guy. If you don't like it, send patches. Yeah. I want to thank the FFmpeg guy on Twitter for inventing that slogan. It's such a great slogan. Fil-C uses what I call the sandwich architecture. So like, if you're using muscle, then the Fil-C runtime, which is libpslow, obviously, is running on top of muscle to get like syscalls from muscle, basically. And that's compiled with just GCC. And then you run the memory safe muscle on top of that, which is just the same version of muscle with some changes compiled with Fil-C running on top of that. And then the rest of the user land is compiled with Fil-C. Key thing is like here in YOLO muscle, when it does a syscall, it's using inline assembly for the syscall. When user muscle does a syscall, it's using Fil-C internal API to go through the Fil-C runtime syscall filters. So even syscalls are memory safe in Fil-C. Yeah, that's right. So like in Rust, if you make a syscall, you're doing an unsafe. If you pass it a pointer with a length that's too big, or you did some bad pointer math, then you're just corrupting memory. In Fil-C, if you do that, you get a panic. So yeah, Fil-C safer than Rust. Rust is the faster but less safe alternative to Fil-C. So yeah, Fil-C runtime features system call filtering, threads, atomics, memory safe signal handling, shared memory. So like, for example, if I were to run a windowing system like Wayland that does shared memory for its frame buffers, that just works in Fil-C. The capability metadata isn't shared, just the data payload is shared, so you can't hurl pointers across the process boundary, which is good, because if you could, then that would be unsafe. Long jump and set jump work in Fil-C. I had to do that because there's so much code out there that uses them for exception handling, and long jump and set jump are completely safe. If you use them incorrectly, you get a panic. Make context and swap context also work in Fil-C. Again, if you use them unsafely, you get a panic. So you can write your own fibers in Fil-C. That just works. C++ exceptions work great in Fil-C, as do all other C++ features. The one C++ feature I haven't ported yet is coroutines, just because nobody uses coroutines. Except for the Nix package manager now uses coroutines. So I'm going to have to implement coroutines so I can have Nix running on Fil-C. So I guess thank you, Nix, for using an obscure feature that forces me to edit. And then you can also do FFI in Fil-C, meaning like you can
Yeah, so the C++ 20 added coroutines, and Phil's joke that nobody uses them is pretty much true, because basically C++ 20 didn't come out with like a good sort of coroutine library. All they came out with was like the language features that would enable coroutines to be used. But you couldn't just be like, oh, okay, so now I can just like whack async on a function and then start like awaiting stuff. No, that would not be the C++ way. So some keywords like co-await and co-yield and co-return were added, and then an execution model was like introduced, and then that was it. It's actually kind of like Clojure-esque, where it's just like, yeah, we're just going to give you the tools to build this thing yourself, rather than give you like a really nice sort of UX on that. And so I've seen various different libraries try to like put all this together in a nice way. But like, here's the single, you know, like they have one example, right? And this ends up being like so much code to try to define like, oh, we have a switch to new thread function that takes some sort of thread and has a struct. You have to create the struct in here, and then this struct is a coroutine handle and joinable, and then thread resuming, and like, oh, and you have a struct here and a promise type, and like, I just like, holy shit, man, you know? Whereas in, I don't know if you've done like Unity, C# coroutines or async Rust or something like that, it's just a lot easier. Or just like async JavaScript, right? You just whack some async on there, and then you put some yields or awaits, and it works, you know? Super easy, barely an inconvenience. One of my friends needed C++ coroutines for something with drones, like 3,000 lines of code because there wasn't really anything. Yeah. So I haven't dealt with C++ coroutines yet either, because I've looked into it a few different times. Like, oh, let's see what things look like, and it's actually like the module system. More people are using C++ 20 modules now, but I think more so than coroutines. But for the longest time, meaning for more than half a decade, it's just been like, yeah, it's not well supported, and it's really clunky, and yeah, I'm just not going to bother with it. Understand that reference? Nice. I'm glad, DJ Blue.
Reflectively make up a function call in Fil-C. Use data to describe what arguments to pass to a function and call it. And all of these things are safe. You can't use them to escape the protections. There are two main distributions you can download, binary distributions you can download, or you can build them from source. What I call the PIS-fix slice, which is just a local installation. You untar it into a local directory, use it from there. You don't need to be root, and it's muscle-based. So you just get muscle, you get libc++, libc++ ABI. It's, if you want to just really quickly test out what Fil-C is like, that's what you use. And then the opt-fil slice is my favorite way of installing it. It's not installed on this computer for a reason I'll show you in a minute. That installs Fil-C libraries into /opt/fil. You need to be root. It's glibc based. And it includes something really cool, which is a memory-safe OpenSSH daemon with full PAM support, OpenSSL, SE Linux, and Kerberos. All of those libraries compiled with Fil-C, totally memory-safe. And Fil-C does support seccomp filter sandboxes, so all of OpenSSH's existing security features continue to work in this model. They're just even better because it's memory safe. So like the next time there's a memory safety bug like regression in Fil-C, you want to be running this because regression would cause just a panic in Fil-C. It would not lead to arbitrary.
Hey, Kuvi. Thanks for the raid. 23 folks. Welcome, folks. I appreciate that, Ray, man. I hope you had a good stream. I don't think we're going to start the video from the beginning for you, though, because we're halfway through. Yeah, we've been watching Phil talk about his memory safe runtime and comparing it to Rust, and talking about how he's protecting against attackers trying to utilize memory unsafety in order to gain control over your process as well as your machine, and that's been fun. Phil has a lot of great insight, and I think he gets a lot of shit online. Like from what I see on Twitter, a lot of people are like, I don't know, they're just kind of calling him out, saying that he's being disingenuous about memory safety and redefining what memory safety means when he says that Fil-C is more memory safe than Rust. and those people are confused. is the nice way to put it. Those people are just confused. I don't think that Phil's redefined what memory safe means at all. I think that he's tackled the problem at a runtime level with an airtight solution rather than trying to tackle it at a language level. And this is, like you can have a language like Rust that is quite memory safe, but when it's still interacting with C libraries, arbitrary C libraries, and still doing system calls that are wrapped in unsafe escape hatches, like the whole thing just ends up not being safe. So yeah, I think his approach makes sense. But hey, that's just me. Maybe I'm being disingenuous in redefining memory safety as well. You're only as safe as your unsafest code? Yeah, pretty much. I mean, I don't want to be unfair to Rust, because I really like Rust. And I think that people who don't use Rust, whenever they see anything about having some Rust code that has some unsafe blocks in it, they're like, ho, ho, ho. I thought that, I thought you wanted to use a safe language, but here I found you had 6 instances of unsafe in your project. Clearly your project is not so safe after all. And those people are also just confused, because the whole point of Rust and unsafe blocks is like, well, if you write it in C++ or C or whatever unsafe language, the entire fucking program is wrapped in an unsafe block implicitly. And then the entire spec of whatever language you're using is in the case of C and C++, just fucking peppered with undefined behavior that says, if you do this, undefined behavior. If you do this, undefined behavior. And like a lot of these things are like not sane defaults, like not initializing struct members that are like integer values. If you just have a struct foo that has an int x semicolon inside, and you just create an instance of foo, like that's not zero initialized. And then if you try to read it, that's undefined behavior. Like there are so many things like stack local variables not being default initialized, and undefined behavior. Phil mentioned like strict aliasing and data races and everything like that. It's just crazy. And so Rust doesn't have a lot of that. Rust does have unsafe blocks so that you can interact with the rest of the operating system world, because Rust is a systems programming language that's built on top of modern operating systems, and modern operating systems are built on the C API, right? They're built on unsafe code. And so in order for Rust to work at all, it needs to have that escape hatch. And Phil he's approaching it from a different perspective altogether, which is like, okay, well, let's take all of that unsafe shit that Rust is building on top of, and let's provide a safe runtime in order to run all of that. Anyway, all that said, I appreciate you, Kuvi. Thanks for always being cool, hanging out. At least in C++, the non-initialization part is for performance. Yeah, I mean, for C and C++, historically, the reason for not initializing, especially like stack local variables or zero initializing the result of malloc is for performance. But I think as DJ Blue was saying earlier, like reliability is more important than performance. Like that's not a good reason. In fact, I think a lot of you have heard me say this before, and I was just tweeting about this not too long ago. There's a mantra that I use. I didn't come up with it. And it goes like this. This is a mantra that I use for basically all of my development. You say, make it work, make it right, make it fast. And I generally say make it work, make it correct, make it fast, but I'm searching for what the original term was. And so this term, well, I can't fucking remember who said it originally. Oh, I don't want your fucking pop-ups. Kent Beck. There you go. I just wanted to say, give credit where credit was due. So make it work, make it correct, make it fast. And so when you make it work, you hack together whatever you want, in order to just get your, whatever feature it is you're working, to actually work. At that point, it's not in a state to where you could actually merge that because you haven't done the next step, which is make it correct. And make it correct is like, okay, I need to make sure that this is going to be maintainable. I need to make sure that I'm using the correct patterns. And I need to make sure that I've done a pass over the code for quality, and that this is going to be something that I'm going to be like okay with merging, into main. And then the third step, which is optional, is make it fast. And make it fast comes after you make it work. It comes after you make it correct. You make it fast. Now, anybody who's working on like garbage collectors, for example, knows when you talk to the researchers that are working on garbage collectors, they're these super smart PhD folks who are coming up with garbage collector algorithms, and you ask them like, well, how fast is it? How does it compare to this thing? And they may have benchmarks they want to show you, but oftentimes what they'll say is like, well, I'm focusing on correctness. I need to make sure that my garbage collection is 100% correct before I can start giving any sort of performance numbers, because otherwise that would be disingenuous, right? And I think that historically it makes sense that this wasn't always the case. Software engineering has changed a lot. Computing has changed a lot in the last, 60 years, man. But that does explain kind of why we're at where we're at, but that doesn't mean that it's justifiable going forward. Also, make it work, make it correct, make it fast. That's a good one. Keep that in your mind. I think having an option to mix YOLO-C and Fil-C would be nice too. Yeah. I mean, ideally you can use as much YOLO-C as you want, or ideally you can use as much Fil-C as you want, wherever, like, and that would be kind of like Rust with the escape hatch. So if that is the profile, the safety profile that you want, then I agree you should just be able to use as much Fil-C as what makes sense for you. I think Fil-C, or I think that Phil talked about this a bit earlier, where like he's saying he had to forego ABI compatibility with YOLO-C And so he just said, okay, yeah, if you're using Fil-C, then it has to be Fil-C top to bottom. You can't dynamically link in YOLO-C into a Fil-C program right now anyway. Maybe that will be possible in the future. I would hope that we can get more people than just Phil working on this so that we can get it upstreamed into LLVM, and then we can get, some bigger companies working on this and funding the working on this. And then who knows where we can go from there. Hopefully the performance profile goes from 4 to 6x range down to, like 2 to 4x range. And that would be quite compelling.
Remote code execution.
Hey, two-step. Watch video 2. Sound like a good approach to memory safety in C. I imagine myself maybe using Fil-C during development and testing to get correctness. Yeah, for sure. I mean, if you combine this with like fuzzing to try to find places where your code might panic, then that would be great. But I also think it makes sense for distribution as well, as long as the performance profile fits what you're trying to accomplish. Like if you just have like I don't know, you're running a service or something like that that's written in C or C++, that's network facing, seems pretty fucking nice to be able to not worry about all of that public network facing API, like being fed in who knows what. I would really enjoy being able to run that on Fil-C.
And then if you want to have a memory safe sudo and a memory safe core utils that don't have any of the new bugs introduced by the rewrites, this is also what you want to use, because I have the original sudo and the original GNU core utils just compiled with Fil-C, as well as a whole bunch of other stuff. So now let me show you the demo. Are you ready for the demo? This was the demo. I am running LibreOffice Impress compiled with Fil-C++. All of its dependencies are compiled with Fil-C and Fil-C++. Yeah, a lot of libraries. So I don't know, what are some big ones? GTK3, ICU, a bunch of xlibs, Cairo, GDK, LZMA. I don't know, I can't list all of them, it's too many. But they're all, CPython, there's a CPython interpreter inside of LibreOffice, because of course there is. Pango, Boost, yeah, that's right, Boost is in there. Boost works great in Fil-C. And on top of that, I'm running on an OS where the entire userland is compiled with Fil-C. So the only, so it's about 94 million lines of C and C++ code compiled through my tool chain and running evidently reliably, right? Like it seems to work. Let me show you. This is the LibreOffice. And to keep it real, I actually made this entire slideshow from scratch in this operating system. So this slide deck was made memory safely. So this is the most memory safe presentation ever. Yeah. Do I have more time, or how am I doing on time?
Yeah, you have more time.
All right, great. So I'll show you more stuff. I'm just launching a Weston terminal. Font size, actually, oh yeah, I should just do this. All right, cool. Font size equals 36, I think. That's what I want. Yeah, there we go. So here is a Weston terminal, also memory safe, obviously. So then let's launch a memory safe, or not .cpp, or sorry, I typed the wrong file name there. Whoops, hello.cpp. There we go. So I'm using Emacs, the full thing with the eLisp interpreter and everything, and it's running C mode here, doing all that pretty syntax highlighting for me. Yeah, it's a hello world program. So let's compile it with Fil-C. So on this system, even if you run like G++, if you run version on it, It's really my compiler. So it's Clang version 20.1.8, Fil-C version 0.681. So I can, compile, hold on. So I can compile this program, hello.cpp. Let's do it with optimizations, because why not? Doop-de-doop. And then we run it. You can see it works great. Now let's look at a program that's not so great. Maybe a program that does an out of bounds. Allocate 16 bytes, and then store at index 67. So then, G++ -o ob.c. So, the compiler does give me a warning completely unrelated to Fil-C, because the compiler has some static analysis for this, but it still allows the program to be compiled. And when I run it, you get a beautiful Fil-C panic.
Wait. That's not a warning. That's an error. Yeah, I think he is Johnny, but he said that he made a joke earlier that his kids do the 6-7 thing, which is why he was doing it. So yeah, I think he's the age where he actually has kids who are making that joke. But hold on. I don't believe that OOB executable was actually created. It wasn't. And the reason is he should have used GCC to compile that C code, but he used G++. And the difference is the C++ compiler versus the C compiler within GCC. And so because he tried to compile that code with a C++ compiler, he ended up with a type error. This has nothing to do with memory safety or anything like that. This is just a type system problem. It's a common problem when you port C code from C to C++, is that C++ will require a static cast from the result of malloc into a typed pointer. And so it's very difficult to read that here because of the blue that is used on the output. But P here is a pointer to char. And malloc is going to return a pointer to void. And actually we see that in the error here. So he got a type error here because you can't implicitly cast a pointer to void to a pointer to char. You need a static cast for that. And he didn't have that static cast. He wasn't expecting to need that static cast because he should have compiled this with GCC, the command GCC, and not the command G++. That's slightly confusing because G++ is part of the package GCC. And that is because GCC originally started as the GNU C compiler, and then it grew into a larger package. I think people just say GCC is the GNU compiler collection now or something like that. But what this means is that the OOB executable he already had. It was already there, and he actually didn't compile that OOB executable right here. I think that I don't think that it's a nefarious thing. I don't think he's intentionally lying. I think that he had the OOB executable from a previous run here. And since he typed this command out manually, he just typoed the G++ into GCC and then saw that there was some sort of warning, and then he remarked on that warning and then just continued anyway and probably didn't even realize. When you're on stage This is the exact sort of thing that you just don't even notice, especially if the next, like your next plan is like, okay, now I'm just going to run the OOB process or the OOB program. If you run the OOB program and it runs, then you don't even realize that anything went wrong. So if he had tried to run the OOB program after G++, and then it failed, like it said, oh, there is no OOB program, then he would have snapped out of like the autopilot mode that he was in. He would have looked back and said, oh, okay, yes, this is an error because I invoked G++, and then he would have fixed it. Anyway, just want to call that out because he said there was a warning, but for Clang and GCC, whenever you see error : that means that like whatever you wanted done, the linking or the compiling, it didn't actually happen. Whenever you see an error like this, it means that like the artifact that you're actually creating here, which is this OOB executable, was not actually created. Wait, I cannot have 1440 on your stream. That's BS. Oh, is that because we don't have... Is that because we don't have Nitro on the Discord? Oh, you're showing a Twitch thing. So you linked to Discord, but you are showing a Twitch thing. I don't know why you can't have 1440 on that. Yeah, I mean, because I stream at I don't know what I stream at. I thought I was streaming at a lot. I mean, it's definitely 1080, but let me see if it shows me here. Hey, Kyle. Hey, Arun. Oh, yeah, it's 2K. All right. Yeah, which is 1440. That's what the source is. But I don't know why you can't have it there, Johnny. I think if anybody should be able to have it, it should be you. But I don't know. I don't know. I don't think there's anything I can do about that. I'll write a letter. $1440 is blocked in some regions. Thanks, Scooby. My man. Yeah. If anyone's gonna know more about Twitch, then it's gonna be that guy, not me. The better streamer.
So.
All right. Now that I've thoroughly Sherlocked this this demo, we can proceed. Some NA VPN. If it's worth routing your video through NA in order to be able to see this at 2K, you can do that. I also heavily agree with Richard's talk, even though I'm not a big fan of rock syntax. Which talk is that? I'm not familiar with Richard's talk. Richard Feldman. Ah, okay. So basically, we just saw it doesn't matter how he tried to protect C if you can't produce artifacts reliably in this language. The whole show is an anti-ad of C now. It's not reliably language, no matter how hard you try to be careful. It looks very sad to me, actually. I don't know what you mean. He intentionally wrote some C that reached out of bounds, and he has a compiled executable where he can run that program that has undefined behavior, and instead of giving the attacker access, he gets a Fil-C safety error. He gets a panic that provides the stack trace as well as some additional information. So what he's saying is that the millions upon millions of lines of C code that exist in all of these applications that have been written over the past 50 years don't need to be rewritten in order to become safe. I mean, he didn't notice the compile didn't work as expected. He doesn't even know he doesn't have needed artifact. I think that you're misinterpreting that. So he had a typo for G++ that should have been GCC, and the OOB binary existed because he had clearly invoked this before. But I don't know if you've ever been on stage, Mark Mondark, but when you're on stage and you're running through a talk like this, it can be very hard to spot some obvious things, right? And so, in fact, I think if I hadn't called this out, not a single person in this stream would have even noticed that there was an error there in that output, and they would have just carried on with the stream. It has absolutely nothing to do with Fil-C or C code or anything like that. This is just a mistake that somebody made on stage when they're doing a demo, which is exactly what happens when people are on stage doing demos, which is exactly why a lot of people don't do live demos. But yeah, it's no shade on Fil-C. It's no shade on Phil. This is just an interesting thing that happened. It doesn't mean anything. You should not give this any meaning at all. The fact that he accidentally typed G++ instead of GCC. It's just a typo that happened in his demo. That's it. It is not sad. And it has nothing to do with Fil-C or memory safety. I don't see your point. You're right. You're right. I don't see your point. I'm glad we're on the same page. All right, moving on.
Fil-C is... Yeah. So the way to read this is it's pointer, comma, lower, comma, upper. So it's telling you that the pointer is out of bounds of the upper bound. And then it's telling you where it happened. You get this pretty stack trace. And then thwarted a futile attempt to violate memory safety. That's the slogan. Let's see what else. I got some other programs in here. There's what's another cool one? Let's do the UAF one. UAF.c. All right. So really simple, malloc free, and then try to store into the object. So let's see. Is this still working? Yeah, it is. Okay, cool. G++ -o UAF UAF.c. Whoa, what's going on here? Oh, I'm trying to compile with G++.
He notices it.
Okay, so whatever. I'll just use CC. It doesn't matter. All of them link to Fil-C. So
he caught it this time, right? So he saw the error. He said, "Oh, what's going on here?" And then he stopped typing G++. Anyway, so Arun, to answer your question, he said it doesn't matter anyway because they all link to Fil-C. And so basically he he has his entire user land for this OS that he's running. Everything is built on Fil-C, and all of the code that he's compiling, even if he compiles it with G++, is linking with Fil-C. Now, how that works, given that he's using LLVMIR for this, I don't know. It could just be that it could be that G++ actually links to Clang++. I'm not quite sure.
I noticed I compiled without -g, so then you get this somewhere instead of the method name. So -g preserves debug info, and so you get actual, where it happened. And boy, is it taking its sweet time to dump the core into my USB stick. That's not Fil-C being slow. That's the kernel not having a bad time with my USB stick. And then, I don't know, I'll show you one more example. Inline ASM. So this...
I think that he does use this as his daily driver, Johnny.
Inline assembly is completely safe. Can anyone guess why in the world you would want to write this inline assembly? Because you could just add in C. So why would you want to do this? Can anybody know? Sorry, I can't hear you. No. No. Yes. Crypto people know that if you tell the compiler, hey, A plus B, the compiler might try to insert speculative branches in there, like, oh, maybe I can optimize this code under this case, so I'm going to if what this is and take different path depending on what the values are. And if that value that you're doing the plus on is like a secret key, then all of a sudden the compiler has introduced a timing side channel. So crypto system writers prefer to either write their crypto entirely in assembly, or they write it in C using tricks like what I'm doing right here, adding using inline assembly. Now, this inline assembly is actually correct. It's saying add the constant 1 to operand 0. Compiler gets to pick operand 0. We're telling the compiler that operand 0 is plus R means it's a register, and I'm going to read and write to it. And I'm going to clobber the control bit, because add sets the control bit depending on the outcome. So if I compile this with Fil-C, inline ASM, let's see, let's enable debug info just to make it. So this.
Yeah, crypto originally meant cryptography, but the Bitcoin folks have reappropriated that, unfortunately.
Works. But what if I mess this up? Like, one way I could mess this up is forget to say that I clobbered the control bit. Oh, that's not what I want to do. There we go. I want to do that, and I want to run it. Now, it's a little weird that I'm catching this error at runtime, but again, send patches. But the compiler finds that, hey, look, you cannot handle this inline assembly because it sets flags, but CC clobber is missing. And if you tried to modify this inline assembly in any other way that would make it unsafe, you would similarly find yourself in this situation.
So I really like, this is, I think, the 4th or 5th time so far in this talk that he has said send patches. And of course, I'm looking at this talk from the perspective of having to give a talk in 2 months at Clojure Conj about Jank, and he's showing off something, some very cool tech here, which is along the lines of what I want to do in my talk. I want to show off Jank. And he's also calling out the places where it can be improved, and that's led him to say send patches. We don't yet do this. We don't yet do this. Like, it only runs on Linux x86 64. Send patches. Seems odd that we catch this only at runtime. Send patches. I like that. I think I want to use that for mine as well, but I would probably tweak it because of the day and age. I would probably tweak that to just say send human written patches. I want to find a nicer way to put that that rolls off the tongue, because it's so easy to. I don't think Phil cares as much about that, and as far as I know, Fil-C doesn't have the anti-AI policy that Jank has, and I know that Phil uses LLMs quite a bit to accomplish the work that he's doing. So that could be why he's not saying it, but yeah, I'd want to figure out how to say that succinctly while still being like a good call to action for my talk. If you guys have any ideas for what the good phrase for that should be, then let me know.
Where that inline assembly snippet will panic at runtime. Or it could even be a compiler error if someone wanted to make it a compiler error. Yeah, well, that's my demo. Hope you liked it.
That's it. Now we're on to questions. I don't really care about an extra 13 minutes of questions, but also feedback. If you're going to give a talk, like rambling on about or like not necessarily rambling on, but like getting into the weeds of like a demo, and then at the end just saying, well, that's it, means that you don't really have like a strong punchline. You don't have a strong ending that's just gonna let people know that you're done. And this is the sort of thing that people do where they'll have a point that they want to convey, and then they'll say their point, and then they'll kind of dance in circles for a bit, and then they'll realize that they don't have anything more to say, and then they'll say, yep, yeah, that's what I think. And it makes, regardless of what you say, regardless of how good your point was, it makes your point land worse. I feel like Phil could have really benefited here from having some sort of wrap up, some sort of summary slide where maybe he just goes back in and say like, okay, so, in summary, Fil-C is a memory safe runtime for C and C++. It allows me to run my entire user space, everything that you're seeing right now, because of how much it supports, and it's far safer than C or C++ or Rust, but it comes at memory performance that ranges from 0x greater to like 6x greater, and then maybe ending with send patches or something like, but wrap it back up, present it nicely, and end in a strong note. Anyway, it's a very cool talk, very cool demo. I mean, it's hard to beat a demo where like the entire software that you're seeing is actually like the everything that you've been seeing on screen is compiled with Fil-C. Like I don't know how you would take that a step further. Still in the era of LLMs, it's so hard to trust people. Maybe you did a great job, but with the same chance, maybe you said Claude, rewrite malloc, sandbox each pointer. Well, Mark, it seems you keep jumping to very like poor faith interpretations of everything that you're seeing. I don't know why. Phil has been a compiler and garbage collection engineer for a long time. This guy's an expert. Like he's worked before LLMs were a thing. He was working on, I think the JavaScript runtime is what he was working on, and like he's sort of well known in that space. So yeah, I mean, he's using some LLMs to accomplish this work, but this guy's an expert. This guy knows what he's doing. So I mean, I don't like that he's using LLMs for this. I don't know how much has been LLM generated versus not, but I also trust that this guy knows his shit way more than I do, and I respect him a lot. So anyway, that's it about Fil-C. I hope you guys had a good time with that. Thanks for DJ Blue shooting me that link suspiciously an hour or so before my stream today. I'm sure it was just complete coincidence. I only trust code. I don't care what others say. That's why it's hard. Yeah, I mean, your life philosophy is going to be whatever your life philosophy is. I think that I would feel pretty like lonely in humanity if I didn't have any people that I felt that I could trust, and that code is the only thing that was trustworthy. There are a lot of people who are worth investing trust in, especially really great engineers like Rich Hickey, like Phil Peaslow. Let's see. I think we're in the mood for a lighting change as we jump into some more coding. Speaking of code, or Linus Torvalds, yeah, I mean, for sure. Linus Torvalds, I mean, lots of people to respect and trust when it comes to code. We were just talking about Andrew Kelly recently. Of course, the old. I mean, it can't even. We'd spend all day listing them on stream. We wouldn't even scratch the surface. We wouldn't even scratch the surface. So what are we doing? We have. I recently broke on I don't know if Kyle's still here, but we have the is jank fast yet I recently broke one of these benchmarks and I want to fix it. Let's see. Yeah. You see how we stopped getting these little cyan, is that cyan? It's kind of, I don't know what this color is, but we recently stopped getting data points for this teal. I broke my code. Your code gracefully handled the breakage in my code. Since Kyle made this continuous benchmarking suite and very impressively made it handle when changes to the Jank compiler don't trust this guy. I don't know if Mark's still here, but so Kyle made this very gracefully still handle when I push breaking changes to the Jank compiler, and I made a change. I made a super fucking cool change, you guys, recently. I'm pretty excited about it, and I'll show it to you. I'll show it to you all, and I'll show you a nice little benchmark as well. And Kyle, I actually have a pull request to add a new benchmark. You gonna look at that, bro? Wait, somebody asked what J16 was. Where was that? Oh yeah, sorry, Johnny. Yes, that is the number of jobs. So this is a common argument to native build systems. So C++, C and C++ translation units are generally compiled in parallel, and so this is gonna use 16 cores. I have 32 cores on this machine, so it leaves half my cores available for streaming and other things. So by default, it's just going to use all 32. If I do that, then OBS isn't going to be able to keep up, and then the stream's going to freeze, and then it's not going to be good. So I have learned, although I do sometimes forget, I have learned to use J16 when I'm on stream. BT dubs, have you already implemented proper initialization with scopes and conditional branches and nested scopes? So we're still doing default initialization followed by copy or move assignment in those cases, Johnny. I've been working on some other stuff. So we have proper scoping done now, but we still have that default initialization problem. I know what I need to do to fix it, but there's been other stuff I need to get to as well. So I've been busy working on lots of stuff. That's just not one of them yet. Okay, so the thing that I did do though, I've been working on a couple of things. So one of the things I've been working on is getting array object support in. That way we can support the closure like toArray and makeArray and aget and aset and alength and a map and whatever the fuck other functions there are in Clojure core for arrays. So that, yeah, TJ Blue's like, fuck yeah. Because the Clojure test suite is... the Clojure test suite is the Jank-driven initiative to test all the Clojure core functions, and Clojure core and Clojure string and Clojure Eden JSON and a bunch of core functions in Clojure. Jank can run most of those that have been written, but any of the collection or sequence-oriented functions, we have tests written for those that use arrays, and Jank doesn't yet implement those. And so that's why I've been looking into adding the array support, because then it's going to allow us to get much better. Like if we add array support and we cover all those functions, we're going to unlock another like dozen or so Clojure test suite functions that we then get to test the behavior of those functions continuously, get a lot more confidence in how Jank is behaving. So it's going to be a big win in order to get the arrays. But I wanted to work on something else over the weekend, this past weekend, because my weekends are my more fun work. Yes, I work 7 days a week. but my weekends I get to generally work on something that's a bit more interesting to me. And so I worked on an optimization, and the optimization is that let me just go like this. This is the optimization right here. This is basically the benchmark that I submitted to Kyle's repo to get it added. So this is originally a benchmark that Bork Dude tried out when he first tried Jank, and he compared the time that this takes in Jank to Clojure, JVM, as well as to Babashka. And Jank was really fucking slow. Jank was really slow at this. And you know what? Let me do a release build. Uh-oh, Mark. Guys, I thought this was going to be about native links too. What are we doing? Oh, okay. Whew. That's cool. We're good. Yeah, Clojure's consistently fucking itself over with its spelling from day one, and now over a decade in, still doing it. I like to write Clojure with closures in my Google Clojure compiler sometimes. That's 3. Do we have more? Oh. I would get Clojure on that issue if I could write Clojure with some closures and compile it with the Google Clojure compiler. There's 4. So anyway, this thing that I did, let me tell you about it. This is the thing that I did over this past weekend. Was I doing this on stream? Oh shit. This is actually what I started on stream last week. And that was to change the literals that Jank has, so that when you have like a 0 here and a 1 million, 10 million, how many is that? 10 million. When you have literals like this, as well as bools and C strings, so normal strings, as well as floating point values, in Jank, these are now just native values. And so this is straight up an integer. And this is just straight up an integer. And so that means that this loop here is just going to straight up be integers. Now, the cool thing is we have inlining for the 0 predicate. We have inlining for inc. We have inlining for dec, so that when we do this here, there is no boxing that happens at all. And this is a big deal. This is a very big deal. There's also no conversion that happens to and from box and unboxed things, because when the Jank compiler looks at all of this, it knows. So this call to 0 ? Is going to be inlined. So we have multiple steps of inlining. We inline it from the var call to the C++ call, and then the C++ call gets inlined as well. And basically all of this just goes away. all of this just goes away. And I want to show you what the result of that is as soon as this finishes compiling. By the way, what happens here? Does Jenk recognize that you assign the same binding I to I in recur and skip that during recur? No, we don't. We don't assign I to I. We assign the increment of I to I. And the decrement of j to j. So let's see. I think we should be good now. Just about. Skip. So if we did a first off, let's do this in closure. So if we did like a COJ, I think -m is what we want, and then we run this. Then we can see we get. So this is, we're not benchmarking right now. We're just doing a single run. If you benchmark this, it's going to be more like 2 milliseconds. Nice hanging out. I'll be back next week. Hey, see you, man. Thanks for hanging out, Arun. Okay, so if we do this, just one run in closure, we get, let's say 10 milliseconds. If you do the same thing in Babashka, then it takes quite a bit longer, right? So 600-ish milliseconds. And if you do the same thing in Jank, now this is using, this is on main. So this is running the latest main. You're like, oh no, it takes 130 milliseconds. That's over 10 times slower than closure, right? Than closure JVM. That's no good. And then you remember that when you invoke Jank, that it doesn't have optimizations on by default. And so then you enable optimizations. And then you realize that it's actually 1,000 times faster. Closure. Oh man. So I have specifically written this test so that the work is not optimized away, because this is a function that takes in a parameter and then converts the parameter to an integer and then does the loop. And the integer is actually a like runtime parameter. So this whole loop is not being optimized at compile time to just using constant folding to go away. So the loop does happen at runtime. No, it doesn't. No, so this is why I'm specifically saying, Johnny, the loop does happen at runtime. But it's a lot faster. So yeah, if we take a look at the code, so here's the actual code for this. We have our parameter n. That's a boxed object. We convert it. So we call int right here to convert it to an integer, and that turns into this toInt. Now we have our result, which is this v4, which we don't actually set anywhere. And then we have these are going to be our mutable values. These are the ones that are going to change for our loop. And so S5 is our I, and then S6 is our J. And so we enter our loop. Now is 0, so our 0 predicate here, this is a call to closure core 0 predicate. This gets inlined, so we don't actually do the var deref. Gets inlined to a C++ function call. The C++ function call has a template that specifically handles like like unboxed integer values as well as boxed values as well as typed box values. So it always gives you the most efficient implementation. In this case, it's just going to check like S6 is equal to 0, like as we're working with an unboxed value. So this entire thing by Clang is then going to be inlined. It will go away entirely. Now, in the case where we're finally done, we have to take I and we have to box it by converting it into an object, but we only do that once at the very end. So what we do for the 10 million times is we call jank runtime increment and jank runtime decrement. But both of these are templates as well that handle the unboxed version, and that gets inlined. And so all of this gets inlined to the point where we're just working on large values. So I think if we were to bump this up, let's see. Yeah, so it does take longer, right? And that's why, let's see. If I add enough zeros, well, that didn't take longer. Is it? Maybe we need to look at the assembly of what's actually going on here. How would this be optimized away if it doesn't know because we're like right here in this code, we don't know what n is. So there's no way that we can, and we don't call it until here. Yeah, I mean, there's no way this can be optimized away because we don't know what that value is, and that's a runtime value. But it seems like it is, because otherwise this would take longer and longer and longer. I just don't understand. I don't see it. But anyway, let's assume it is, because it does seem that way right now. It does seem that way right now. But the main thing is, I don't want to get sidetracked on that because it doesn't matter. What matters is, the main thing is that we, by changing our literals to be, make it swap an atom. No, that's going to be so slow. Like swapping an atom requires thread synchronization, everything like that. It's just going to kill everything. But guys, focus, focus. The thing that matters here is that because we made the literals into native values, and then because we have the inlining of these templates, we have the inlining of the vars and we have the inlining of the templates, all of that ends up to be very easily optimizable by Clang. This is huge. This is so important because it means, we didn't do a single type hint here, right? I guess we converted this guy to an int. What if we don't? 1, 2, 3, 1, 2, 3, 1. Go back here. If we don't convert this guy to an int, so J here is an object ref, the results are just going to be drastically different. Now we're talking 10 milliseconds, right? So if we convert this guy to an int once, and then everything else remains an integer. This is an integer, and then we support unboxed operations on this. Then we're able to get incredibly fast. That's great. That's huge. That means that so many of just your general day-to-day arithmetic number crunching and everything like that in Jank is just gonna be faster. It's just gonna work faster. Yeah, we don't have an easy way to look at generated assembly right now. Like we could take this in like a just-in-time way. We could take this and we could AOT it, and then we could take a look at what's inside. I don't know what any of that is, so let's just do that. And then I don't care about that. I guess I don't really care about this either. And so let me delete that and then do, actually I'm just going to delete this outer and then change this to a defen, and then I'm going to call this stuff. And then we can take a look at we'll do a defen main args stuff 10 1 2 3 1 2 3. Let's try this. I'm just curious. So we'll do compile module path temp AOT. We'll do an O3 on that. That was not the file that I thought we would be getting. Why? Why is that? So that's, I think, what was in here before. If we undo all of this, no, that's not even what was in there before. Where are we? Wow, what happened here? So I want to compile module path is temp. I want AOT. It should grab temp AOT.jank. What? Oh, is it because of a dot out? Is it not actually going to a dot out? Are we going to? Yeah, we're not going to a dot out. That's why. What are we going to? Target a dot out. Whew, okay. Yeah, so with AOT, this ends up being a lot slower. But why? When you just-in-time compile this, yeah, I don't know. There are already AOT performance differences that I haven't looked into yet. But looking into the, so this is why I wanted a JIT sort of way of looking into the generated assembly of things. Like we can already look into the IR, the jank IR. We can look into the generated C++. But I want to look into both the generated LLVM-IR as well as the generated machine code for a particular function. Because there's something to do with the just-in-time compiling this. So if we were to AOT compile this, we're using O3, we get 52 milliseconds. But if we were to instead do run main, we get 52 milliseconds. Why? Right. What's the difference? What if I just run this? Run temp AOT. 52 milliseconds. But what was the difference here? Is that we have a function call with a direct invocation. And here we're going through a var. So if we have a function call, if we have a function here with a direct invocation of this, like that, and then we time that. Ah. Okay, and then we wrap this in a function. Foo. And then we call foo. And we use run main. That ends up being fast. And then we do this and we compile. And it ends up being slower. So yeah, there's something interesting about JIT compiling these things, and I don't yet know what it is. But JIT compiling in general with Jank leads to better performance right now. Oh. I think I know what it is. I think it's the inlining. Yeah. So if we were to take a look, so we're gonna have target. We're gonna have this guy here, and if we do an object dump of target cache x86 8 out. Oh, I want object dump disassemble. So what was my function called? Function was called stuff and foo. Very, very helpful. So here's stuff. Mm-hmm. Mm-hmm. So first off, we see that there is a lot going on here. But I'm not seeing calls to... I didn't see any external calls here, but we are seeing a lot of calls. So there's probably just some... There's just some probably address trickery going on for those external calls. But yeah, what I really want is to be able to get the assembly dump for what it looks like when you JIT compile. And then also what I really want is to be able to get this, same performance profile with the JIT compile as well as the AOT compile. I believe that the reason why the AOT compiled stuff ends up being slower is that the way that the Clang JIT compilation works is that all of the code that you feed in ends up effectively being in the same translation unit as all of the other code that you JIT compile. And when you have code that's in the same translation unit, you get more easy inlining. And so I think that when we compile the code For AOT compilation, we don't get those added benefits. And I think that what that means is that all of those templates that we have for the math functions, they don't end up getting inlined the same. This is my theory right now. I don't actually have a good reason. I don't actually have like a clear idea right now. Something I still got to figure out. 5G technician, I missed the Fil-C watch. What were your thoughts? Fil-C is great, and people who shit on Phil and Fil-C and say that he's redefining memory safety and is being disingenuous about Rust are confused. Can you LOT for AOT? Yes, but we don't yet because it's complicated. But we will. I don't know if we're going to be able to get to that before the conj. I really want to. I have big plans for a lot of the AOT optimization stuff. I have such cool plans. I just need the time to be able to work on them. And yeah, I mean, already Jenks AOT to static binaries or to static runtime is over 20 times faster to compile than Graal native images. The file sizes are about half the size of a Graal native image, and it uses far less memory, and it still starts up instantaneously. But that's without LTO. That's without like tree shaking. That's without any sort of escape analysis or additional inlining that we can do on our end before LLVM, before LTO. There's a lot. There's a lot that we can do. And I have plans to tackle all of that. PGO, I don't have plans for PGO. You get it for free with the LLVM. Yeah, I think that we should probably get, like, it depends how you want to run it. If you want your PGO to be part of like your JIT stuff, and then you want that to apply to the AOT stuff, we're probably going to need to do some additional work. That might be a nicer UX though, to be able to like jank run or line run your stuff and then have like have some PGO instrumentation going on, and then when you AOT compile, then you can use that. Like I don't actually think LLVM supports that right now, but that would be a really cool direction to go to. And then there's like the more typical PGO workflow where you AOT first with instrumentation, you do your runs, and then you AOT again. And that would probably be more straightforward to hook into. But still, I think comes afterward, because like having to AOT with instrumentation and then run your like expected workload and then AOT again based on that is a pain. Like I don't actually know in my career with C++, I've never actually seen anybody do that. That's not to say people don't, because I know that people do, but PGO in my experience is like not as commonly used. But yeah, so for JIT compilation, clearly this is doing some additional optimizations, and appears to be removing the loop as well. But yeah, I have a note to get LVMIR printing for functions as well as assembly printing for functions in the Jank compiler namespace. We already have a tool in there to get you like the native code for any given function. Anyway, I've entirely gone on a tangent to show you guys this stuff that was happening, but it's not actually what I wanted to work on. So we're gonna reorient, get back to the stuff we wanted to work on. So the thing I want to do is I want to fix the ray tracer, and the ray tracer broke when we did all of this. Literal, like native literal work, and that's not something I caught because the entire test suite, all of our different test suites, unit testing and functional testing and end-to-end testing, didn't catch whatever error the ray tracer actually caught. And it wasn't until I looked at Kyle's continuous benchmarking, which I look at every now and then. It's not until I looked there and I saw that we stopped having entries for the ray tracer that I realized, like, clearly we broke that. So let me get this debug build going again, and then we'll try running that ray tracer. We'll see what happens. We'll try to pinpoint that and figure out what the actual issue is. Maybe it's going to be super clear. Maybe it's going to be sinister. We'll have to find out. But I'm going to refill my water and then hit the restroom, and then I'll be right back. All right. Meanwhile, I've almost devoured a protein bar. All right, so when we try to run the ray tracer, we get an error in a template instantiation in math. I think that was 833. Okay, so we're doing min, and we have a less than here for a small integer ref and a double. 829. You need if else. Yeah, I believe I fixed that on my other branch. Else if. I know C++, I swear. If else. Yeah, I have another branch that I think you saw already. I'm working on DJ Blue for the seekable sequence-like open object model stuff. I believe that I fixed that there. One of Max's also has this. Now let's take a look. Yeah. Yeah, it shouldn't matter too much because they all have returns in them. But it is more correct. Is more what we want. But yeah, I saw you say DJ Blue, so like, so that's why I had the PR to add those templates into math for is0 and inc and dec. And yes, absolutely. So like having those templates and having them handle the unboxed values as well as the type erased box values as well as the typed box values, that is what allows that whole thing to be inlined. And that's what allowed, in this case, that whole loop to be alighted, is because we had a nice template that had a nice implementation, you know, specifically for the, like, that's optimized for the types that we're working on, that can then be inlined. So we want that for everything. Like, especially for math stuff, like every single one of those functions will be like every single one of these math functions that we have should just be a template in here, because there's no, like, if we're ever going to pay the cost for having things be templates, it should be for this sort of arithmetic stuff, because the performance benefits that we get from it are just huge. Open object model. Will we be able to implement new jank runtime object types in user code? Yeah. Yeah, we will. So The the old object model, Kyle, was based on a tagged union. And then we used these visit style functions. And so we had visit object, and then we also had visit number like and visit seekable and visit map like and some others that just have big old fucking hard coded switch statements. I can't actually jump to those right now. I don't know why. But they just have big old switch statements like this. That it's some template that takes in some function and then calls that function based on the switch of the object. So we cast to that type and then we call the function with that type. And so that means that whenever you do like a visit object and you give it like a generic lambda, we'll instantiate that lambda like 60 times, once for every different object type. And this had a big compile time cost in order to generate all of that code for each of those different instantiations of the lambda. But it was really great for runtime. Like the runtime performance was superb because we didn't have any virtual dispatch. All we had was a switch-based dispatch into a function, into that instantiated lambda that had a tailored implementation specifically for that type, and it had full type information. So once we did that switch-based dispatch into the instantiated lambda, from then we don't need to do any additional dispatching because we have the full type for whatever object we're working on. And that was great. That was really nice. But the problem with that is it doesn't work if you want to be able to have people define their own object types, because it requires a completely closed model. And the problem that I saw this problem and I wanted to find a way to fix it, but fixing it in C++ is quite difficult because this was a problem I had early on where, and I wrote a blog post about this. So we had Janklang blog. We had faster object model. So this was, back in 2023, I was already looking into this where if you just have a Jank object as your base, and then, Jank string is some struct that inherits from Jank object, and then has some string data, then already in order to implement this like function to native string, you need to have a vtable pointer, right? Inside your Jank string. But then as soon as you want to start adding behaviors on top of that, like, let's also have some Jank countable thing. And so Jank string is a Jank object and it's also Jank countable. Then now you have two vtable pointers. And so that makes not only every object another, 8 bytes larger in size, but also it makes the initialization of those objects every time you do a new even slower. It slows down based on the number of interfaces you have. And so I was looking at like how this was going, and this is the way that I started because this is the way that Clojure JVM is implemented, is that I had a Jank map that inherited from object and then seekable and countable and metadatable and associatively readable and associatively writable. And I realized that like, wow, the size of these objects is just fucking exploding. And the time that it took to allocate these was like a big problem. And so I switched courses. I went to a closed object model and did a bunch of benchmarking, explored different types and everything like that. But that only lasted for so long because eventually I hit the point where I'm like, well, if we want people to be able to define their own record types and define their own structs that behave as objects and everything like that, we need to open this back up. But I took a couple of years to try to just, I guess, of hammock time to try to figure out how I wanted to do it. And what I settled on was that we were ultimately doing this the wrong way. The way that Clojure works is based on common abstractions. So you have seeks, you know, and you have numbers, and then you have like map-like things and whatnot. And I was focusing on object types, but I should have focused on object behaviors. And so what I ended up doing is I moved, the big thing is, rather than having a bunch of different interfaces that you inherit from, the object struct has every single one of those. And so the object struct by default has virtual functions for all the object-like things, and then it has virtual functions for all the calling, and it has virtual functions for get and find and refs, and in my new PR, like seekables and sequence likes and like all these things. And so basically the object, the base object type is going to have everything, every possible, so like official object behavior is going to be inside of the object. But by default, all of these functions are just going to throw an exception that says like, oh, I don't support that behavior, right? And so the default behavior of setValidator is just to throw an unsupported behavior exception for ref-like. You know, I don't have ref-like. And then there's also a bit set. And so right now, the way that I have it is that each object has a bit set, and the bit set is based on these behaviors. And so the behaviors in the bit set tell you which of those virtual functions on an object are actually implemented. And so there's a predicate called hasBehavior, which I don't know where it is, but it's on the object. Right here, hasBehavior. And so hasBehavior checks given it an object behavior or a set of them, if you want to OR them together, and it'll tell you whether or not it has those behaviors. And then based on that, so that's not a virtual function call, which means it's going to be, you know, much faster. And then based on the result of that, you get to choose whether or not you want to then do the function call, or if you just want to handle that some other way. So this allows you to, at runtime, more easily and efficiently check, is an object capable of doing a get? Is it capable of doing a compare? Is it number-like without having to do a visit? And so we're still using virtual dispatch, but we get away from the problem of having so many different vtable pointers because we only have one vtable pointer. We have one vtable pointer to object, and then all of the virtual functions are in object. So we also remove the problem of having so many vtable pointers. Hopefully that was interesting to somebody. But yeah, that basically allows us to open up the object model without having to pay the huge performance cost of having all of those different interfaces. Now the key limitation is that the official behaviors are limited to what we can fit in this bit set. And so, realistically, that means that like we probably can only have 64 different official behaviors. But I took a look at the number of behaviors that there are. Do I have that here? I cleaned up my notes here recently. I wonder if I actually, damn. I don't have that, but I looked at all of the behaviors that are in Clojure JVM, like all of the interfaces that they have, as well as all of the concepts that we had previously on the Jenk side. And it's something like 30-ish. So I feel like 64 is a lot of space that we could potentially work with. Implementation aside, it will make wrapping C++ types much easier than so many opaque boxes. Yes. But we're going to need official support for defining objects in Jenk syntax. And I also have plans for that in both defining functions as well as types using Jenk code. So that way you can just define native types and inherit from whatever you want to inherit from and override whatever functions you want, define all of that inside of Jenk code. And this will allow you to port even more C++ code to Jenk code in your Jenk files without using CPP raw. And it will allow even more of your Clojure code if you want it to be like, I really don't like the word performance, so I'm gonna try to get around that. If you want it to have even better performance, you're gonna be able to move that code to structs and then move those functions to C++ functions that are statically typed, fully statically typed C++ functions. All that just defined within your Jenk files, but all of that also being able to easily call any of your Clojure, Jenk functions, and then vice versa. They'll all just work together and also all be defined in the same file. Gives you a lot more control over your performance profile. You could do stuff infrequent behaviors into you could also stuff infrequent behaviors into the 63rd bit if necessary. Yeah, I think that we'll have a lot of flexibility, and I'm still porting all of these over. So like right now we're still using the old visit format, as well as some things have been ported over to the open object behavior format. And I have a big PR open right now that moves seekable, fresh seekable, sequence like, and sequence like in place. These 4 new behaviors all into the open object format, and it goes through all of the visits and moves those over. But like even then we're still under 10, so I'm not worried about that. We'll handle shuffling those around or being clever with those as we get to it. Okay, that was today's a tangential day, but we're back here now. So DJ Blue, I saw that you were saying that maybe this should be typed L data. I think that you're right, because all these are typed L data. So this was 833 was what we were at. And this is object ref. So we visit it. We have a fully typed thing. I think that this should, just be typed L data. Max has the same problem, BT dubs. Okay. So Max, this guy doesn't right here. This guy doesn't. This guy does. Okay, so let's address both of those, and then we're gonna have. We have a debug build, so compiling won't be so bad because we don't have to do phase 2 compilation. Maybe that's it. Maybe that's all we needed. And then if you're wondering like how that ever worked in the first place, I think that some of our types actually implement these operators, just not necessarily with all the right combinations of things. Yeah, for our custom types, getting all those operators supported is a real pain in the ass, as you can see by these. But it's worth the effort because, as I was saying before, these that's the type of thing that you just really need to be fast. And so you want the most efficient implementation of all of those math functions. Cool. So now this runs, and we're in a debug build of Jank, and we're also running this without optimization, so it's going to be super slow. I'm just going to let this run the first time through, because right now we don't have eager compilation on, which means it's going to be JIT compiling some more stuff as it goes. Which is why there's this long pause here, because it's actually started to do the ray tracing, and then it's going to find that it's going to try to call those functions, and they haven't actually been JIT compiled yet. So then it's going to do a whole bunch more JIT compilation of all of the different ray tracing functions, and then we'll get our first output. And then after we have our first output, then our second output will come much sooner. But yeah, it looks like we're fine. So let me get out of here and jump into here, and then ray. Cool. And cool. So push that up. Now we can get a pull request open for that. Nice. Open that pull request. Okay, moving on. So I was talking about your gotcha. Thanks, DJ Blue. I appreciate you, dog. You're doing incredibly useful and important work by fixing all of those tiny issues that can be hard to spot, but prevent Jank from passing all those functions. And you deserve more credit than you get. So thank you. Let's see. So I think I changed to this visit branch, and then, yeah, we're compiling. That's fine. Yeah, so if we take a look at the object now, for these behaviors, we have these new behaviors here. I think I'll actually just get rid of fresh seekable and merge that into seekable, because there's nothing that's seekable that's also not fresh seekable. So there's no point in wasting a whole bit just for that. Thanks. You're welcome, buddy. So the reason why, while we build this, the reason why I started moving these seekables and sequence likes and everything like that into the open object model is because we have to do it to support arrays, and that is probably not obvious to start with, but the reason is that the array object looks like this. So it's a template, and then it's an array that inherits from the base object, and it has some pointer to a t, and then it has a size as well. Basically looks like this. Now the problem with this is that although it's baked into the compiler, because it's a template that's going to be instantiated at runtime, we actually don't know all the types that an array can be, and then also the object type of an array is just array. So you may have an array of ints or an array of floats, an array of whatevers, and they're all just going to have the object type of array. And this is because C++ doesn't have like runtime type reflection. So we don't really have a good way of saying, okay, yeah, this is an array of ints, this is an array of floats. So instead we just have an array object. And then the way that we interact with that array object is we use the interfaces. So things like get and nth and so on, so that we can then access the data. Now there are problems with this, and this is a very frustrating problem, and it is exactly why I have pushed arrays back as far as I have, and still haven't tackled them until now. And actually, I started tackling them on stream almost a year ago, and then, well, at least 6 months ago. And then in the middle of it, was like, yeah, I can't do this. There's still some shit we got to figure out before I can do this. And the reasoning is this. So there are two sides to the coin for arrays. On the closure side, we have an array object like this. And it can be any normal, like it can act like any other object, meaning you can put it inside of your persistent data structures, and you can print it, and you can get a sequence from it and everything like that. But we're limited by the actual interfaces. And so let's take, for example, the interface for something like, we don't have nth here, I think. Yeah, we don't have nth here, but so we'll just have to use get, and then you'll just have to like pretend that I'm, I don't actually know if arrays support get with indices the way that vectors do, but nth would effectively be the same. So don't worry about it. Let's say we have a virtual function for like nth that looks like this, and maybe we even unbox the index, right? And so it looks like this, and Jenk will automatically handle the unboxing of that if needed. And hey, we even have native literals now, so we don't need to do that by default, right? And so since we need this behavior, to be generic and work with any sort of container, any sort of collection, it needs to return an object ref. That's like all of these things just return object ref. And this is exactly, it's what call just takes object refs and returns an object ref. This is exactly what Clojure JVM does. It takes in JVM objects, it returns JVM object, right? But this means that if you want to access the nth of something, of some array, that you need to be able to actually turn that value into an object ref, and that you need to pay the cost of boxing that or trait converting that every single time you want to access that. And so that sucks. That really sucks, because if you wanted to be able to like loop over an array or something like that, and keep doing an nth access, you're gonna need to grab out all those values and box them. Can we make a get generic? Well, the problem is that you oftentimes you don't know the type of the object that you have. You just have an object ref. And the only way that you would be able to get the full type is to do some sort of visit or something like that, right? Which we don't have anymore. We're getting rid of that. And so all this stuff needs to be polymorphic instead. And so what we're left with is, and now remember I said there are two sides of the coin. We're only talking about one side of the coin right now. Now, the frustrating thing about this problem is that both sides of the coin suck in some way and are great in another way. And as far as I see it, and you guys can tell me, please tell me if I'm wrong. I would love to be wrong here. I've thought about this for fucking months, and I have not found a way to do this. So the one side of the coin is we have this boxed jank object that's an array, but it's still a template, and it holds a pointer to the data and some size. Now, it implements these interfaces, but it means that whenever you go through those interfaces for things like nth or get or whatever, you need to box. And so what I would end up doing then is I would end up putting a requirement on here. I would say requires, and then, like I trait convertible t, right? And so we would need to make sure that you can only have an array of some t that is trait convertible. And ideally you do that with things that are just really easy to box. So things like integers and doubles and bools are great to box because they don't actually require allocations. So we have we did the whole NaN boxing stuff, right? To where you don't actually need to box integers unless they're greater than int32s, and you don't have to box floating point values at all. And then bools, we just have pre-allocated true and false objects that we just grab references to, so you don't actually need to do any new allocations for those. But if you're doing something else, like an array of some custom type that you provide a trait conversion for, then whenever you try to do an nth on that, you're going to end up doing an allocation to do the actual trait conversion. That sucks. So that's the one side of the coin. We can get an array that's an object that can work, but it has trait conversions whenever you're trying to do interface with it, whenever you're trying to do interface functions with it. Now the other side of the coin is the C++ side. Okay, so now the C++ side is, well, we have syntax in Jank to be able to just create arrays, just dynamically allocate like straight up arrays, right? And so you could do something like, let me grab all this away. you could do something like array, and you could do like a CPP new, and then you could say array of int 256, right? This will give you a new dynamically allocated array of 256 integers. This works. And at this point, this is a C++ value, right? You just have a dynamically allocated C++ value that you'll need to do a CPP delete for, unless you put that inside of some sort of in some smart pointer or whatever. But this is not going to work with any of your closure functions, right? You can't like easily map over this. You can't easily print this with print line, and it decays to just a pointer to an int. So it's hard to add special support for arrays, because arrays in C and C++, or at least C style arrays anyway, are like they really easily decay, and so they're kind of indistinguishable between like a pointer to an int versus an array of int. You kind of have to treat them like a pointer could be an array as well, or it could be a pointer to a single int. And so you have this choice of, okay, well, on one side of the coin, I can have a jank object. It's going to work with the rest of the closure sort of ecosystem, but I'm going to have to pay a cost every time I actually want to grab things out of it. And then you have the other side, which is, well, I can have just a straight up C++ array, dynamically allocated or stack allocated, and I can do whatever I want with that from the C++ side, but it's not going to play well with the closure side of jank. And I have not seen a way to make it so that we can actually have both. Can JVM closure return a primitive from aget? So let's take a look, because now we're asking interesting questions, right? Let's take a look at, oh, not that one. We got a third-party closure. So if we core.clj, if we jump to aget, then what we see is what the closure JVM does is it uses this closure lang reflector prepret. And so this is a hint to the JVM to say, hey, we're going to be returning something of this type. And then it uses this array get. Now, array get just returns an object. It just returns a boxed object. But this whole like reflector thing tells the JVM, because the JVM is very dynamic and is able to do this runtime reflection, tells the JVM that object is actually of this type, and that helps. So the other thing that you can't do with the array object side of things is that you can't actually get a typed pointer to the data. So we could add a virtual function that returns a pointer to void that's part of the interface for arrays, called like, get raw data or something. But we have no idea what the type of the data is that you're going to want. And so we're going to have to just, as part of the interface, we're just going to have to give you a pointer to void. And so at that point, the polymorphism really gets in the way of dealing with typed arrays on the closure side of jank. And then interestingly, this inlines, to just take this a little bit further, aget inlines to a call to runtime aget. And then to answer Kyle's question even more, runtime aget has different overloads. So we could do this as well. So we could overload. So if you do have a typed reference to an array of float, then we could definitely do these overloads. But the general case is going to be this one, which is you just have some array. We don't know what type it is, and we're just going to give you back whatever object is inside of there. So yeah, the JVM is special because it treats arrays as normal objects. And so an array itself, an array of ints, an array of bools, what doesn't matter, is itself an object. In C++ and in C, like an array of anything is just an array of anything. It's not there. You know, there's no common base for that, and so it doesn't fit well into the object model. So my plan for this, since it seems like both of these use cases are good to be able to want to like create just native arrays. We can do that already. I want to improve our support for native arrays with the Jank type system analysis and everything. So there's work I need to do there. Yes, so we want to be able to support native arrays, but then the other side is, I think it also makes sense to want to support array objects and have those work with the closure side of things. And so I'm currently doing both. I'm currently planning to do both. We'll have an array object, and you can use that if you want. It'll work well with the persistent data structures and everything. And then if you also just want to make a native pointer, then you can just do that. And then DJ Blue, I'll answer your question because it also ties into this. And then if you wanted to put that native pointer inside of a CPP box, which is just an opaque box, then you could do that if you want. So the HyperSE, hi, doing well. Welcome to the channel. Is named Jank because it's self-deprecating and it starts with J. DJ Blue, CPP unbox. So the opaque boxes just store a pointer to void, and then they also store a string of the type info. CPP unbox needs to specify the type at compile time that you're expecting to pull out, which then we turn into a string, and we do a string comparison of the types, the type that's in the box as well as the type that you expected. If that all checks out, then we pull the type out and we cast it. And so that's exactly what CPP unbox does. Boxing doesn't seem too bad. It's what would happen in Python NumPy. You just prefer to use the vectorized operations in NumPy. In Jank, you could implement performance critical array ops in C++. Yeah, so I mean, ideally, it doesn't have to be written in C++. Ideally, for the performance critical stuff, then you could do it with just the C++ style of array rather than the array object, because there's no boxing that's going to happen with something like this. And I want to support like array style initialization, so that way, if you wanted to pass, for example, 256 values here, then you could, and then also, as I mentioned, improving our type system support for these arrays in different places. But yeah, it just doesn't seem like we can do any better than that. Can we have the same limitation for CPP get? If you want to get the value unboxed, provide. So DJ Blue, for CPP-A get, there's no concern for boxing. Because the CPP-A get is for native arrays. So that would be like this. So we do a CPP new for our array here, and then if we do a CPP-A get A0, right? For CPP-A get, you have to know the type of the array. There's no dealing with a boxed array. CPP-A get statically at compile time is going to know that that the first parameter is an array or is a pointer. That has to be the case. It's only for the dynamic side of things, which is, so this is the C++ array, and then this is the Jank object array, where you do a make array int 256, and then you do an A get A0. Why can't the dynamic one also have a version of A get which is parameterized on return type? So the first, you could add some type information after the fact, but the whole point is, if we don't know the type of what A is, right? So let's say we're in some function, we have some function, we receive parameter A, right? And we want to be able to do an A get on it, right? Here A is just an object ref. We have no idea what type it is. We don't even know if it's an array. We know that A get is going to try to treat it as an array. And so A get is going to check if the object type is an array. And then it's going to, but even if we know the object type is an array, we don't have something we can cast to, because we don't actually know the type to go to, because it's an array of what? We have no idea. Yeah, and so even if you type in the return value, you still have to go through an object ref in order to get there in the first place. And so that doesn't actually solve the boxing. It just adds the type information back on at the end. But the whole point is that the having to go through the trait conversion in the first place is the problem. So DJ Blue, you're saying if you have a cast A get type, yeah. So if we did a cast A get and then type A int, so we have a problem. So first off, types are not first class values in Jank. They are in the JVM, because the JVM has runtime type reflection, but C++ doesn't. And so types as values doesn't really make sense in Jank. And what that means is that cast A get cannot be a closure function. This ends up having to be a CPP function. This ends up needing to be a special form that has its first parameter and type position. Yeah, if you have a box, so what Kyle said, if you have a boxed array, then you can unbox it as an array, and you don't even need to specify the size there. You know, you could just do like a pointer. So you could do something like, you could do like a CPP a get, and then you could do a CPP unbox pointer to int, and then you have your a, and then you grab 0. Now with this, we'll have all the type information that we need. So if A is a box, we'll make sure that, you know, A is a box. We'll make sure that what's inside is actually an array, and then, or is actually a pointer to an int. And then when we do a CPP A get on that, we'll know the result of that is going to be an int as well. And so there's no sort of trait conversion that has to happen there. Yeah. So this will definitely work. And this, honestly, this should work today. But the problem is that if you want to support like make array, to array, and the other closure core functions that work with arrays, then you need an array object. And if you have an array object, then like all of this stuff doesn't really work. Are we feeling like arrays should always just be opaque boxes? Like, so if you do like a make array, if you do like a make array int 256, so already make array would need to be a macro because it's taking int, you know, type position. It would need to be a macro for some C++ thing. Right now, the way that I have it is that it's basically a macro for this. It does a CPP new like so, and then it does a like jank runtime create array. I don't know what it's called, but it's called like create array or something like that. That takes in the pointer as well as the size. And this gives you back an array object. I think what we could do is, instead of having an array object, we just have an opaque box that has the pointer inside. Yeah. Yeah, the box is opaque. Yeah, so if you wanted to do like a count on it or something like that, then you're not going to be able to. Yeah. And so this, yeah. So like I keep jumping back and forth on these and like trying to see how I could make, how I could have one solution and have it work in like all these cases. But it always just seems like we really need both. Like we need to be able to have an array object that you can just create and then deal with the boxing. If you want to use the closure style APIs for that, but you're able to print line it and you're able to get a sequence, you know, from it, and it feels like closure data. And then we have the C++ side, which is like, well, you could just straight up allocate an array. You could put it in an opaque box, like you can put anything, any pointer in an opaque box, and then you can just do CPPA get, CPPA set with it, and all of that stuff is fully typed. But I don't think it makes sense to combine CPPA get with the dynamic like jank box. It's weird. Seems like part of this is for folks who want to port existing Clojure code. Seems like if you're writing it for jank specific code, you probably just use the opaque thing or use a vector. So Kyle, in your example here for as raw array, is a is a jank object? A is one of these array objects here. So this would, so like opaque box, the only way that this would actually work is if we store the type as like a string in here. And so we would have to do like a string type. And then when you do an as raw array and you specify the type that you want, we would need to then compare the types and only and throw if the types don't match. But if they do match, then we can get you a raw array. And DJ Blue, that was basically what you were saying? So the nice thing about this is you still need both, right? You have the jank object array, and you also, like, if you just want to go straight up native arrays, you can. If you want to put them in an opaque box, you can. But also, if you've gone with the jank object array, we provide you a pathway to get to a native array by using this like as raw array or whatever we call it. Yeah. When did you expect jank code to use boxed arrays, CPP arrays, and vectors? So I wouldn't expect most jank code to use vectors. Unless they're working with a library that needs vectors, just because they're not going to be easy to pass around, right? So C++ values in jank are generally, they're just lexically scoped to a particular let, and Clojure vectors. Okay, my bad. My bad. Different answer then. So yeah, I mean, vectors, Clojure vectors will be the default for any sort of ordered data. And then if you need an array, I think that the choice between going with the native array versus going with the boxed array is just going to be based on like how easily you need that array to integrate with other Clojure data. Like if you want to have a closure vector of a bunch of arrays that you're like passing around, you know, or like a closure map of keyword to array, then that's going to be, and if you want to be able to like really easily print that or serialize that to Eden or something like that, it's going to be a lot easier to have an array object than to use an opaque box. If you have a native pointer in an opaque box, we don't know what's in there. You know, we can't print it. We can't check the size of it. I mean, when you print it, it's just going to say, yeah, I'm an opaque box at this address, you know? So the jank object arrays they're gonna feel like closure data. And then the native arrays that are inside of opaque boxes, those are gonna be a lot leaner. Why wouldn't you just use a closure vector? So yeah, the question is, why would you use a closure? Why would you use a jank object array versus a closure vector? And then the answer to that is, if you need that data to be contiguous, then you're going to use an array. And also, like in Closure JVM, we use arrays if for performance, right? So like if you're like rapidly mutating an array, it's going to be significantly faster than if you're rapidly mutating a persistent vector. It's going to be faster as well than if you're rapidly mutating a transient. Arrays are just a lot more primitive, a lot more efficient to work on in terms of like cache locality than especially if they're larger than 32, which is the size of the chunk of like a persistent array, which is the same sort of chunk that transients work on. Yeah, so there are different performance scenarios for even object-based arrays compared to persistent vectors or transient vectors. Maybe it would be really helpful to have like a breakdown of like, maybe we even want like a flow chart or like a decision. What are those called? Those decision charts where it's like, if you want this, then do this. Otherwise, do this. And then do you want this? Okay, then do this, and then this. To help you decide on the data structure you want to use. Because yeah, going from, you'll have like closure persistent vectors, closure transient vectors. You'll have like C++ standard vectors. You'll have the jank array objects, and then you'll also have the native arrays. Decision matrix. I don't think it's the matrix. It's actually like a. It's a visual. It's not a table. It's a visual graph. Yeah. I hear you. Okay. So, Kyle, I think you were helping DJ Blue with the array ref stuff. Thank you for that, because yeah, it's like I think what was being proposed is not something that was viable given the C++ type system. As a related aside, can we specify types to templated functions from Jank? Not yet. That's something that it's something that I've looked into supporting, and I know how it needs to be done, but it's kind of a pain in the ass. But it's gonna. We'll probably go through a couple different iterations of it. The first one is just gonna like be making it work, and then we'll see how we can make it nice. But yeah, right now it's not viable. Right, or I mean, right now it's not doable with the syntax. Make it work, make it nice. I kind of like that. It's not as on point as make it work, make it correct. But it is. Maybe this is why the original make it work, make it right is good, because right means different things depending on the scenario. Either it's like it has the right UX, or it has the right design, or it has the right code size or whatever. I think maybe that's the disconnect for me. If we could specify a type to the generic function, would this be easier? No. I think that the disconnect for you is around the C++ type system. Because the thing is that with the jank object, like once this array object of T, once this becomes an object ref, you have no way of getting this back into a typed array object. Yeah, like once this becomes an object ref, you're done. Unless, as Kyle said, unless you know the exact type that you want and you can cast it. But there's nothing that's going to tell you that type. You have to know it ahead of time. You have to know it at compile time. If you're fine specifying the type, then why not just use an opaque box anyway? And then you don't need to pay the cost of having it in a array object. I guess to defend your point there, the benefit would be you get to treat it as closure data. You get to print it nicely, everything like that. Arrays have an additional metadata? Arrays don't have metadata. No, they don't have closure metadata. Yeah. Make it totally rad. I like that. Array type over opaque box because I still want to use closure core functions on it for convenience and only unbox it for perf. Yeah. Yeah. So we need a way, as you were saying, Kyle, to turn those array objects into the raw arrays. I don't know if we need a new special form for it, which is like as raw array, or if we just have a virtual function on object that's implemented by array that just gives you a pointer to void, and then you can cast that to the type that you want. That would also work. The benefit of doing it with your suggested approach is we store the string type alongside it, and then we can check the type at runtime. Yeah, I like the benefit of that because the UX for the CPP unbox with specifying the types is really nice. And if you get it wrong, then we get to show you, where you got it wrong and what the actual type was. That's pretty nice. I see. Okay. That's good to know. Array style predicates like bytes, question marks? Yeah, is that a function? Yeah, so we could check here, is the object an array? Does it have the object type array? And then we're gonna need to have, we're gonna need to have another virtual function then to get the element type, or as they're calling it, the component type of the array. Which is then basically returning the string type. Exactly, Kyle. So we're going to need a virtual function that returns basically that string type for the array. And then we could check that here. I don't know if these functions make sense. Like these they cast the value to an array. Like I don't think this makes sense in. Maybe it does. Maybe we do the same check. Like we do the bytes question mark predicate here, and then if it is the case, then we'll do a cast to the typed array ref. Hey Eric, stopping by to say howdy. I'm glad you stopped in, man. I hope you're doing well. Hope your week's going well. Yeah, I guess we could do these. I think that can work. But oh man. All right, let me get rid of this. So yeah, so what we got out of all this was do we have arrays here? No. Array. Yeah, so we need and then Mm-hmm. All right. So yeah, that's arrays. And then on the native side, I got a lot to do to clean up how arrays are handled, because we have issues with like casting between array types and null pointer, and decaying arrays to pointers, and stuff like that. But yeah, I think once we get arrays on the Jank side, as well as clean up the arrays on the C++ side, will be basically where I want for language features for this year. And then the rest of the work is going to be on error reporting, source information, stack traces, that sort of stuff, because all that's pretty shitty right now. Yeah, so I think that being able to define C++ functions and structs and globals, I'm hoping we can get done this year, and then that will play into the open object model. I think that being able to define those C++, like that C++ stuff, really easily within Jank files without using CPP raw is going to be crucial for like porting C++ code to Jank, as well as unlocking the C++ performance profile within Jank applications. So that way, if like you're like, oh, this closure way of doing things is not fast enough, you know, I need something more, then you don't need to go to a separate file and write it in C++ and link it in as a library or anything. You can just write a C++ function in Jank code, and then call it right there. So I'm hoping to get that done this year as well, because I think that's going to be big. I don't think that'll be done before Conj though. That'll be post Conj. All right. Well, I was gonna do some work on this stuff, but I think all the work that all the brain juice I had for work was spent talking about arrays and working through all that with you guys. But it was really useful for me. So thanks for working through that with me, because I've been thinking about this for a while, trying to find how to make it all work. And there are some real benefits to being on like the JVM or something like that, where you can just fall back to, well, everything's an object. And we just do not have that luxury in the C++ world. So anyway, I'm gonna wrap it up and then go rest my brain. But things that are going on. So we're doing this array stuff. We're porting more stuff to the open object model. We got those type literals, and then as soon as this, so I'm gonna build out all this array stuff that we talked about. We'll see next week if I'm still working on that. If so, then you'll get to see some of that. But after this, I'm gonna be putting a lot of work into improving. So I got like source info, stack traces for runtime errors, and error reporting for C++ sources and candidates. So like if you call a C++ function and you don't quite get the arguments right, right now we don't give you any information about like what overloads there are and where they are inside the C++ source, and what the types of the parameters are, and what the, like how that corresponds to the types of your arguments. And I want to make all of that really great. But that's going to involve a lot of work with Clang to be able to get the source information for all those things, and try to identify like which types match and what conversions are being used, and implicit conversions and explicit conversions and trait conversions. It'd be really great to be able to spell out like all of those things. And then make errors really, really clear, to just give you all the information that you need in a really nicely presented way. That's basically going to be implementing my own version of C++ error reporting using the info from Clang. I think that's going to be a big task, but I think it's absolutely going to be worthwhile, and it's going to show that Jenk can improve not only on Clojure's error reporting, but also on C++'s error reporting. So we'll try to build on both of those. And then I also have some secret work that's been going on that I'm going to be revealing at the conj, and I'm not going to talk about until then, because it's going to be a big reveal. So we'll have to wait until that happens. But yeah, until then, I'm going to go rest my brain and replenish my brain juices. Thanks everyone for hanging out. This was great, productive. We got to learn a lot about Fil, and then we got to jump into some Jenk stuff. I appreciate you all, and I'll see you next week. All right, adios.